And we can go ahead and get started. Hello, everyone. Thanks very much for joining. I'm Jeff Sale. Today, we'll be having a 3.5-hour tutorial on the Comet to Expanse transition. We have several presenters, and I'm sure it's going to be a great presentation. Before we get started, I would like to point out the Exceed Code of Conduct. Everyone is expected to be on their best behavior, but if anyone observes any inappropriate conduct, the links are here, and you can reach out to exceed.org code of conduct for that. We would also like to emphasize that we're committed to providing training events that foster inclusion and show respect for all. This is a very important effort within the Exceed training community to minimize the instances of inappropriate documentation. And with that, I will go ahead and hand it off to Mary Thomas, who will be sort of the master of the proceedings. Take it away, Mary. Oh, not master.
Mary, you're muted.
I am muted. I am now unmuted. So Jeff, you have those slides, right? If not, I will share. There we go. Let's go to the next slide. So the goal of this tutorial or this workshop is to show you guys what you are going to have to do a bit differently on Expanse, and there are some differences. The architecture is different. The operating system is, we're now using CentOS, but we're using Slurm, but the module environment's a little bit different. So today we'll just try and show you the new features on Expanse and get you familiar and move on to the next slide, please, Jeff. So the next slide just shows our schedule. And I'm not sure that it got posted to the website yet, but we'll start with Mahidar. He'll talk about an overview of Expanse and talk about Slurm. And then we'll have a short break, and then we'll talk about modules and another break, and then job charging and using the Expanse portal, a new application running on Expanse, and interactive computing, and then we'll wrap up with data transfer mechanisms. If you have questions, type them into the chat. We'll have people that are working and supporting the speakers to answer any questions you might have. And with that, let's start with Mahidar to do overview of systems and allocations.
Thanks, Mary. I'll start by sharing and hopefully get the right desktop here. Okay. Can everyone see the slide okay?
Yep, looks good.
Great. So yeah, I'll start off with a Expanse system overview, and then go into, in the second presentation, I'll go into how to run jobs on Expanse. So the outline of the talk, essentially just introducing the system, look at the system architecture, specifically look at the AMD EPYC processor architecture, the hardware details, the NUMA options, and basically how to use them, and then look at some of the innovative features in Expanse itself, and then talk about allocations and summarize what we look at. So Expanse basically is a result of an NSF award. It's basically a Category 1 capacity system. The PI on the project is Mike Norman, and a lot of us co-PIs there. And then basically the primary vendor for the system is Dell, Aeon for the storage, and then we have a lot of other components, processors from AMD, the Intel processors on the GPU node, the host processor, the NVIDIA GPUs, and the Mellanox interconnect. So it's a system that's made up of 13 scalable units, and I'll go into a little detail on each scalable unit in the next few slides. There are 728 standard compute nodes, 52 GPU nodes, and each GPU node has 4 GPUs, so you have a total of 208 GPUs. We have 4 large memory nodes. So if you think about it, this is basically similar to our setup on Comet. So it's you can almost see the evolution coming from Comet to Expanse. In terms of the data, we have a 12 petabyte Lustre file system, which can do about 140 gigabytes per second on writes and 200K IO operations per second on the metadata side. Actually, it's much greater than that. And then as we've had on a lot of the SDSC systems, we have node local NVMe storage for fast IO local storage. We are going to have a 7 petabyte Ceph-based object store. This is not going to be available right at the beginning because we are essentially going to restructure some existing storage. So that's going to show up sometime next year, but that will be an additional storage option that will be available on Expanse. So the quick overview of the compute side and of the system itself, we looked at all the numbers. So overall, it's 93,000 compute cores. So you almost double the Comet core count. And based on the benchmarks we've run, we expect close to, more than 2x the throughput over Comet. Most of the applications will see a per core improvement over Haswell. We see anywhere between even performance with per core going out to almost 1.8x on some applications. So it really depends on the application. And since the nodes have 128 cores, so on a per node basis, you're going to see a pretty large improvement in performance. And then given the 2x core counts, the throughput's easily going to go over 2x. We expect a smooth transition going from Intel to the AMD processors. We've compiled and run most of the common software packages, a lot of benchmarking, and it seems good so far. And whatever feedback we've got from the early user testing kind of confirms that. People seem to be happy with the system in terms of running and compiling. And right now, the system is in early user period, as I mentioned. We expect production in November. It should be pretty early November. And the operation is scheduled for 5 years. So let's go into the rack scalable compute unit. So as I mentioned, basically 13 scalable compute units. Overall, we are looking, so let me go to the next slide actually. So each SCCU is essentially designed to have full bisection bandwidth within the rack. So you have 56 compute nodes, which amounts to a lot of cores. So it's 7,168 cores compared to Comet, which had 1,700 cores in a rack. We also will have 4 GPU nodes in an SCCU, and all of it's connected through with our HDR switch. The HDR switch has, it's a 200 gig HDR switch. So what we are doing is splitting the cables to get HDR 100 to each of the compute and GPU nodes. So what that does is gives you the 60 connections down to the nodes, and then 20, and then 10, 200 gigs going up. So it's effectively works out to a 3:1 oversubscription. Each of these standard compute nodes is 2 AMD EPYC 7742 processors, 2.25 gigahertz. They are 128 Zen 2 CPU cores essentially. And it features PCI Gen 4, 256 gigs of RAM on each node, and that's DDR4 3.2 gigahertz, I think, and a terabyte of NVMe. So you got a lot more space per node, but you also have a lot more cores per node. So something to keep in mind when you're running is to use the local scratch if you if you have an IOPS heavy workload. On the GPU nodes, we have 4 NVIDIA V100s. It's 32 gig GDDR on each V100 GPU, 1.6 terabytes of NVMe. As I mentioned, there are Intel CPUs on the GPU node. And then going out to the network diagram, you can see basically you have 56 compute nodes, four GPU nodes, and then the uplink of 10x 200 gigs. Overall, the network plugs into a lot of the external fast networks listed out there, so which is similar to what we had on Expanse, but we have a 25 gig connection on each compute node, so you can get quite a bit of external connectivity. So next, let's look at the AMD EPYC processor architecture. So it has 8 core complex dies. So if you look at the picture on the right, you have each of these CCDs has 8 cores essentially. And there is a IO die in the center, which is at 14 nanometers, and the CCDs were at 7 nanometers. So this kind of an innovative design lets them pack in a lot more cores, and through the IO die, there are multiple ways of kind of booting up this node in terms of NUMA domains, and I'll talk about that in the slides coming up. So each of those core complex dies, so this picture on the next slide is one of these green CCDs in that diagram. So there are 2 core complexes on each of them. And each core complex has 4 Zen 2 cores, which share an L3 cache of 16 meg. There's a lot of L3 cache on this machine, so it's 256 megabytes of L3 cache total. Each core also has a private L2 cache of 512 kilobytes. And so now you can kind of see that there is a hierarchical setup there. Basically, you have the IO die, you have the CPUs split off into the CCDs, and then each CCD has 2 core complex dies with the affinity, with the shared L3 caches. So in terms of how these can be booted up, there are several options, but you can essentially do NUMA domains on each socket, so multiple NUMA domains. And for the HPC workloads, the best option is to do an NPS 4, which is 4 NUMA domains per socket. And the way this works is the processor is partitioned into 4 NUMA domains. So you have 2 CCDs and 2 memory channels in each of the NUMA domains. This lets you, if you do the binding right, you can kind of get scaling out to all 4, the full socket, because of the memory channels being split this way. The PCI devices will be local to one of these NUMA domains, and so the network card could be on one of them, for example. So the main thing to keep in mind is that there is some complexity in the in NUMA domains. So this is just on one socket, remember. So then you have 2 sockets that gives you another level of non-uniform memory, right? So you have to be really careful when you're running jobs on the system to be binding and using the layouts the right way. So there are several compilers available on the system. So we've tested applications with AOCC, GNU, and Intel compilers, and with MPI versions, we've got MVAPIsh2, OpenMPI, and Intel MPI. Right now, we don't have any defaults because what we found is, depending on the applications, different sets of compilers work better for some and worse for others, kind of. So you should test out things. For the applications we are installing ourselves, we primarily stuck to the GCC compilers and then used AOCC where appropriate, where it was better performing, basically. This is a moving target, is what I would say, because there's a lot of optimizations going on these processors, and we are involved with a lot of different uh, sites which are running AMD processors, and also with AMD themselves developing application recipes. So things might change, but you have a lot of options right now. So as I mentioned, at runtime, it's very important to bind correctly. So you can, for MPI jobs, basically use a pin domain if it's Intel MPI, or if it's Open MPI, just do the mapping. You can also use Slurm directives to, Slurm options to essentially bind the right way. And we are actually developing some tools to help out, especially for pthread codes and for hybrid MPI OpenMP cases. So we will have an IB run and an affinity script available. So the type of applications we've run on Expanse, we've gone through quite a few benchmarking efforts, basically run Chromax, NAMD, Neuron, OpenFOAM, Quantum Espresso, RackSML, WRF, and so you can see there's a broad range of applications that we've tested, and kind of different application areas, all kinds of combinations. Overall, what we've seen is performance ranges matching on a per core basis to almost 1.8x faster on a per core basis. On the GPU side, we've benchmarked some of the MD codes like NAMD and Amber, and also a lot of the machine learning kind of codes. What we've seen is greater than 1.5x per GPU improvement over the Comet P100 nodes. And for some codes, it's closer to 2x. It's 1.85 to 2x for Amber, for example. So that actually brings me to the GPU node architecture. So it's 4V100s, as I mentioned, 32 gigs on each V100 GPU. The host node itself has basically 384 gigabytes of RAM and 1.6 terabytes of PCIe and NVMe. And the processors on the node are Intel Xeon 6248s, which are basically cascade lakes. And if you look at the topology, you can see that the 4 GPUs are split between the 2 sockets, and the numbering is odd even in terms of all the even numbers are on one socket and the odd numbers on the other socket. So you can see the numbering there. And then you have NVLink between the GPUs. So that is a difference from Comet. So on Comet, if you had to talk between 2 GPUs on different sockets, you would have to go through the host CPU and through across. But now with NVLink, you should have much better performance, I think. So in terms of software stack, we'll support a pretty broad application base. We're trying to replicate what's on Comet with a lot of the packages. We commonly used packages in bioinformatics, molecular dynamics, machine learning, quantum chemistry, structural mechanics, visualization. We'll try to get things on. You may not have your favorite package on day one, but we can definitely work to install as people come online. We have a pretty big chunk of it replicated already. So today's talks basically are aimed at informing you about basically the differences going between Comet to the Expanse application environment. Marty is going to talk a lot about the modules and the setup. For those who are curious, the main mechanism for installs we are using is SPAC. This lets us leverage a lot of the work that's been going on in the SPAC community to port and develop a lot of the HPC software stack. And AMD has its own fork of the SPAC base, and they are putting in performant application packages into that. So that's an ongoing effort. So as things become available, we'll update them with the AMD versions so that we get the best performance. We will continue to support singularity-based containerization on Expanse, just like on Comet. So if you've been using containers on Comet, you can do the same on Expanse. So some other so Expanse in addition to the standard way of the standard compute nodes and GPU nodes and the Slurm-based scheduling also has a few innovative features. So we have an option to integrate with public clouds. It of course needs a lot of work. So this is something that would be done essentially on a project basis and will require some interaction with SDSC. So it's not a push button kind of thing. But we have demonstrated this with work on Comet, and we're going to replicate that on Expanse. Basically, you would be able to use Slurm to submit your job, and then there's a whole infrastructure to make that work seamlessly so that you end up running the job on a cloud resource. So early work was kind of used for running Cypress jobs from the gateway. This approach is cloud agnostic and kind of will aim to support most of the cloud providers. So there are options behind in the back end. Basically, you have to look at data movement, data in cloud, lots of different things to look at. So if you're interested, this is something that you would have to request additional support for. Similarly, we are also looking at composable systems. This is so that we can expand beyond the boundaries of what's available on Expanse as hardware. So for example, you may have some pieces that are available on Expanse, some pieces that are available on a public cloud or a different resource. And what we are trying to do on Expanse is to be able to carve out some of the nodes using and set up a Kubernetes cluster on that, and then basically federate with other Kubernetes resources outside of the system. Again, this is going to be needing like a little more advanced support, so you would need to request that as part of an XRAC request, and also make sure that there is a case to do it. So this is not something you want to do lightly. It's more if you have a workflow that actually needs something like this, then you can definitely make this happen. So then in terms of the rest of the support mechanism, so we have Expanse is going to be integrated as an Exceed level 1 resource. So you can have the support coming through the Exceed ticketing system as you had on Comet. In terms of transitioning, we have an overlap of 6 months between Comet and Expanse, or rather now it's 5 months, but quite a bit of overlap. So we can definitely work on the transition with a lot of users. And today's workshop is essentially the first in a set that basically will help you transition from Comet to Expanse. As I mentioned, you'll have advanced support available for cloud integration and composable systems. We're also starting a new program, the HPC at MSI, targeted at minority serving institutions. So we can award some discretionary time that lets people get on the system in a rapid fashion. And will support such projects. So in terms of allocations, Expanse will show up as a resource right now on Exceed extract windows. So if you're looking to submit proposals, that's one of the options. So there are 3 resources that are related to Expanse. There's the Expanse CPU, basically, which is the allocations on the compute part of the system. Expanse GPU, which is basically allocations on the GPU V100 parts of the system. And then we have allocated project storage. These are allocations on the Lustre file system, essentially. And the file system is available on all the nodes of the system. Note that it's a single file system that's split between Scratch and projects. So the total allocated space that we can do on the project side is at least at this point is around 5 petabytes. And note that we will have a per project limit of 50 terabytes to begin with, so that, no. So in terms, and I should add that any storage allocations have to be justified in terms of why you need that for the duration of a project. So it's meant to essentially keep data for basically files that you expect to need for the duration of a project. So any Scratch space should just go into the Scratch section of the file system. I have a few snapshots of the allocations page, basically how you can log in and where the Expanse options are. Basically, you'll see the Expanse Dell cluster with AMD ROM, and then the GPU and the storage piece. So to summarize, basically, Expanse will provide a huge increase in performance and throughput compared to the Comet machine. And it's essentially an evolution of the Comet design with some innovations in cloud integration and composable systems. And some of that work was started earlier and kind of continued evolved into the production side of Expanse, essentially. We will have integration with Open Science Grid, so that's another piece that would allow jobs on the machine. And we looked at the architecture of the system, basically the 728 compute nodes and 52 GPU nodes, and the HDR100 interconnect on the nodes. As I mentioned, it's going to go production in a couple of weeks, essentially. And you can follow all things Expanse at this website. So I think that puts me right at almost 11:30. So we can probably do a few minutes of questions. Let me see if I can pick out the chat. I'm going to stop sharing and look at the chat to see if there are questions.
Yeah, Marty and Trevor have been handling it, except for the last question. There's a question specifically about the project storage.
So Ron, you had a thing that you have projects, but the directory is different than the directory.
Yeah, I think the question about the project storage is it's possible. I mean, these directories are created manually right now, so
Okay,
it's possible
yeah.
we just if you're already on the system as part of the early user access program, maybe we have not created it for you. So if you want to send us a ticket, that would be probably the best way to go about that.
And I think, Paul, there was a question on your question on Globus. Yes, we have a exceed pound expands endpoint set up, so you can use that for Globus transfers. And we have enabled sharing on that on specific directories, so you can also do Globus sharing if you're on that endpoint.
So Mahid, can I ask a question?
Sure, yeah, go ahead.
Yeah, so could you give me a little bit more explicit sense of how a Comet research allocation right now transfers to Expanse? I mean, I would just assume that like within a couple of weeks, if we have a research allocation on Comet, we'll be able to run on Expanse. Is that right?
No, actually, that's not true. So what we are doing is people have actually asked for Expanse explicitly in their allocations because this has been available in an allocation cycle for a while. I think it's been available the last 2 allocation cycles. So there are actually people with Expanse allocation specifically. For Comet users who have an allocation that goes beyond the end date of Comet, which is true for a lot of people, we will transfer them to Expanse when we get closer to the end date of Comet. Now you can always request a transfer from Comet to Expanse if you would like to use Expanse, and that is totally fine. Or you could ask for a supplement on Expanse, and that is also fine.
I see.
But we are not
to
automatically
make-
transitioning every Comet allocation to Expanse, if that's the question.
Okay, good. And so that kind of transfer is how you do that is found under.
So it's like a regular
under-
exceed transfer between resources.
Okay, great. Thank you.
So I think there was a question about whether there's a purge cycle for Scratch. Yes, we're going to have a 90-day purge from create time. So and the project space is where you would keep something that you need for the longer term. That is for the duration of a allocation. I should say both the locations are not backed up. So if you have critical data, we always urge you to make offsite backups of anything that's critical. All right, so I think I will transition to the next talk, which is running jobs on Expanse. So let me go to the front of this thing and start sharing again. So again, for completeness, I have a system overview and again in this slide deck, just in case somebody picks up this slide deck offline. So I have a system overview, and then we'll just look at the login info. And after that, what I'm essentially focusing on in this talk is looking at the Slurm scheduler, the partition info, and how things are a little different than Comet and how things are similar in some cases. Then we'll look at just running jobs examples for MPI, OpenMP, hybrid cases, and GPU jobs. I'll go over the file systems a little bit and also give you some example scripts to use local Scratch usage. So let me go that. So that was the architecture thing I was talking about. So since we just went through that, I can quickly go over it in case somebody just joined. So basically, Expanse has 13 scalable units, 728 compute nodes with about 93,000 plus cores, and then 52 GPU nodes, which have 4 V100s connected with NVLink. It's for a total of 208 V100s GPUs. There is HDR 100 connectivity into the node, and then the switches at the top of the rack for each of these racks. There are basically HDR 200 switches. So overall, we get a 3:1 over subscription between the nodes. So let me skip through that. So logging into Expanse. This is basically very similar to what you're doing on Comet. The allocations are different for CPU and GPU resources, just like on Comet. So like when you get an exceed allocation, you would have a separate allocation for each. However, the login node is the same. So you can log in to login.expanse.stsc.edu. So if you have an SSH client, you can just directly SSH using basically your username. I think I missed one question on the previous talk where somebody asked about if the allocation IDs will be the same. If your project is the same, yes, it'll be the same. But there is a tool, and I think Nicole's going to talk about it, which basically lets you get information on what your allocations are. So anyway, and your user, and the reason this came up to me is basically the username is also basically going to be the same as what you had on Comet. So you can directly log in and use your Exceed portal password, or and this will basically put you on one of the two login nodes, login 01.expanse.edu and login 02.expanse.edu. Both nodes are identical. You can also log in via the Exceed single sign-on host, so login.exceed.org. So you can basically SSH with your Exceed portal username to the login.exceed.org, which has two factors. So if you've got your two-factor setup with Duo there, you should be able to log in there, and then GSI SSH to login.expanse.sdsc.eu. One other new thing on Expanse is we will have an Expanse user portal, and Subha is going to talk about that later today. So that's another mechanism of accessing Expanse. You can basically submit jobs from that user portal. You can also use some of the interactive programs through that. And there's more details coming in Subha's talk there. You can use SSH keys to essentially enable access from authorized hosts without having to enter your password. But make sure that you have a strong passphrase on the private key on your local machine, and don't copy that key around. keep it on your local machine, and you can always do you can use SSH agent to avoid repeatedly typing the private key password on your end. But whatever you do, don't do a passwordless thing, because that's a huge security problem. And if you are for some reason, like say, have a programmatic thing that connects via SSH very frequently, we do have a limit on that, and you might get blocked for a little bit. But if you do have this use case, please email us so we can give you an option that lets you avoid the problem. And there is a security webinar that Scott did a little bit ago that kind of goes into some of these things from a Comet perspective, but most of that applies on Expanse too. So the first thing is the appropriate use of login nodes. So login nodes are meant for like file editing, simple data management, like moving files around, or copying some small files remotely. That's okay. But main thing is you should be using minimal compute resources. So don't run jobs on the login node, even if they're meant to be short, because if 10 of you do that, that's enough to slow the login node down. So please avoid running on the login node. And then all computationally demanding jobs, even if they're interactively run, should be going through the batch queuing system. So don't use it for anything computationally intensive. Don't use them to run some intensive workflow management tool, because that's going to cause problems too. And essentially, if you're doing some data transfer, if it's a small amount, that's okay. But if not, please use one of our data mover nodes for doing any intensive data transfers. And preferably, you should use Globus for the big transfers, because it'll give you an efficient way into the system. And do not run Jupyter notebooks on the login node. And Mary is going to talk a little bit about how to run those appropriately. And also don't set up servers on the login node that provide services to the outside world, because that could lead to issues too. The one other big difference, I think, between Comet and Expanse is the GPU nodes, as you may remember from the earlier talk, basically have different CPUs. So if you're doing compilations for the GPU nodes, it's best to request an interactive session and do a compilation, since this host CPU is different. The other thing that's different is the stack on the software stack for the GPUs is different from the software stack for the CPUs. So that's another reason to essentially get a GPU node allocation and then do the compiles there. So in terms of scheduling, so Expanse uses Slurm just like Comet. It's a much newer version of Slurm, so there are additional features and additional strict enforcement of limits and so on. So, and I'll talk about that a little bit. But the usual Slurm commands will work. So submit jobs using sbatch. You can check your jobs using sq. I encourage people to use the -u option so that you're not querying everyone's jobs at the same time. That thing slows things down and also causes an additional load on the scheduler. It's easier for it to deal with specific requests. So, and if you want to cancel a job, you can use the scancel command. So let's look at what's similar to Comet and what's different from Comet in terms of the partition. So just like Comet, we are going to support both exclusive and shared partition. In terms of what's common with Comet, like you have the compute partition, which is essentially CPU nodes exclusive access. One real thing to keep in mind is if you make a mistake and put a shared, like a 2-core job on a compute node, there's a huge cost to it. So please be careful in terms of how many cores you need and if you really need the 128 cores from the compute partition, because you will go through your SUs real quick if you make a mistake and run on the compute partition. And we've seen this happen on Comet, and we typically catch that, but yeah, it can lead to a much bigger penalty in this case because of the higher core count. We obviously can't refund that because the jobs are blocked, blocking those resources when you do that. In terms of shared partition, so these are the shared partition is for CPU nodes and for jobs that need less than 128 cores. Similarly, on the GPU side, we have the GPU nodes with exclusive access in the GPU partition, and then the GPU shared partition if you need less than 4 GPUs. Just like Comet, we have a large shared partition for the large memory nodes, and a debug partition for short tests and quick access. So what's new on Expanse? So a few things. One is there's a GPU debug partition, which I know will make a lot of users happy because it was one of the things that was asked for a lot on Comet. So we do have a GPU debug partition. So this is essentially for short tests and compilation tasks. We also have preempt partitions, which basically discount discount the SUs used and so that you can run on the nodes if they're free, but the jobs can be preempted by jobs in other partitions like compute or shared, for example. Similarly, we have a GPU preempt partition.
Mahidar, can I jump in here for a moment?
Yeah.
There's been a lot of activity on the chat, and it can be a challenge for some of our
Okay.
attendees to be tracking both at the same time. So if you have a minute or two, can you review briefly what's been going on? Some of it has already been covered by you, but the questions.
Okay. Let me go back there. I might have to stop sharing and go back to the thing. Okay. Let's see. So I think there was a comment about switching to node hours on the SU definition. I think the reason we didn't do that is because of the shared partitions, basically. Because then you would end up with fractional SUs, which I don't think we are set up to deal with right now. And then so there's a question about memory usage being enforced for shared nodes. Yes, it is. And I'm going to talk about that a little bit further down. Yeah. So there was a question about the transfers basically going between Comet to Expanse. So if you're intending to transfer basically in the March timeframe, you don't really have to do that because we're going to do that. That transfer comment was more meant for people who want to immediately use time on Expanse, since we are not automatically moving the Comet time right away. So if someone has Comet time today and wants to use Expanse mid-November, they would have to put a transfer in.
So yeah, I'm not sure how much more time we need to spend on that,
Okay.
but appreciate taking a bit of a moment for people to get caught up on both.
Oh yeah, sure. I think hopefully everyone's caught up. And
yeah, and Marty and Trevor have been doing a great job.
thanks. So back to the partitions. So this slide basically, and Nicole's going to cover this again when she does the charging aspect of it. But basically, what we have.
Hey, Mahi, you need to share your slides.
Oh, hold on. Thanks. All right, very good. Looks good now?
Yes.
Okay, great. So yeah, so this is a quick overview of basically the limits. So we have a 48-hour limit, just like on Comet, on the partitions by default. So some of the limits are, so one thing I should say is that these limits are what we kind of thought of looking at, like the performance numbers and kind of this, the sizes of the jobs that typically run, and we kind of put those in. But they are flexible, and if it turns out that some of these might need to change, they will be changed. But right now, these are the limits we are going in with. So the max number of nodes you can request on a compute partition is 32. So that gives you basically 4,096 cores. And so that's quite a bit more than what you had on Comet in terms of number of cores per job that you can run. And so you can have a maximum of the 64 nodes running your particular group's jobs. And the reason we have these limits is because 64 nodes is essentially nearly 10% of the system. So we are trying to balance the system out for all the users. Similarly, on the shared compute side, we have the equivalent of 32 nodes essentially if you run one core. So you one single core jobs essentially. So you will end up with 4096 as the max running jobs. Similar things on GPU side, we have a max of 4 nodes for a GPU job. Remember, these are V100 nodes, which are quite a bit faster than what we had on Comet. So this is equivalent to like 8 nodes, I think, on a Comet side. So that's where we came up with the limit. But this is something that may change it depending on what the utilization looks like and how the queue wait times look like. One thing I should note is that the GPU nodes have already been fully allocated based on what I've seen of the allocation requests so far. So, so these will be busy, I think. And then on the debug partition, we have a max of 2 nodes per job, and the 2 nodes is just so you can test an MPI job essentially. deliberately kind of stuck a lower run limit on the number of jobs because on Comet we have noticed people kind of trying to game the debug queue a little bit and roll through a lot of jobs, so we have a lower limit. And as I mentioned, we have the GPU debug partition now. So a few other things, basically on the Expanse scheduler side, we have a few required parameters. So first thing is the partition, the -p option or the -- partition option. We would like you to put that in explicitly. On Comet, I think we defaulted to compute. So this is something you would want to put in. You would need a number of nodes, and the number of tasks per node or the number of n tasks, right? One of the two needs to be specified. The Slurm will pick n tasks if you specify that. And the wall clock time, it should be specified explicitly. And then two other things. One is the account. Unlike Comet, we are not going to pick a default. So you will have to explicitly set this account on Expanse. And then on the GPU side, if you remember on Comet, we were setting --gress. So on Expanse, it's a --GPU, which is the total number of GPUs needed by the job. One other critical thing to note, and this goes to, I think, Kenneth's question on memory. So --mem, --mem CPU or GPU, one of these parameters, they're not required. However, the default is quite low. It's 1 GB per core. So it is recommended basically to explicitly request this, even on compute and GPU partitions. So you're not going to get 248 gigs on the compute partition if you don't ask for it. And this version of Slurm is quite strict with all the, I mean, the way we configured it, it's quite strict with basically enforcing all the limits, including like the topology of your request. And I'll talk about that in a bit. But this is a big change. So you kind of need to get in the habit of requesting some memory parameter. So it could be mem or mem per CPU or mem per GPU. So I'll start off with the interactive jobs, and you can do srun just as you did on Comet, and that will give you interactive access to the compute nodes, and then you can run through the scheduler, whatever you need to. So again, one thing that I added in red here is basically you need to specify the account. So let's go into some sample scripts to see if anything's different essentially compared to Comet. So simple hello world MPI job here. So if you look at the parameters, most of them are pretty standard, right? You have the job name, you have the output file. Usually we tag that with the job ID and the name of the first primary compute node so that it's easier to track down issues later for us. So we recommend doing that because if you have a problem with a job, the first thing we ask you is what was the job ID. So it's nice if it's in the output file's name. And then yeah, you have the partition, the number of nodes and the task per node in this case. You could do n task if you want. And I highlighted the memory per CPU. So in this case, I put in 1800 megabytes. So it's 1.8 gig essentially roughly per task in the per CPU in this case. And then the account, as I mentioned, is a required quantity. Now, I'm not going to go into the environment piece a little so much, but since Marty is going to talk about it, but in your job scripts, I think you should get in the habit of basically starting off clean and loading exactly what you need. So do this in your job script instead of your bash RC, especially on Expanse, because the GPU nodes and CPU nodes are different stacks, and you can't really load both of them in the bash RC. So do not put any module loads in your bash RC unless you're absolutely sure that that's not going to conflict with something else you're trying to do in the batch script. So in this case, basically, as you can see, I'm purging. And now one other difference, and I should have made this red, and I will in the final slides, is you do have to load the slum module. So slum is not in your default path, like it's on Comet. So you will have to load that module. And that is needed if you want to use a command like srun in your MPI job, for example. And also for MPI runs because they are integrated with the scheduler. So you would need the module load slum. And then the module load CPU here, what it does is sets the module path to the CPU stack, essentially. So as I mentioned, it's different on the two sides, so you have to load that explicitly. And then it's like the usual, like you're loading a GCC compiler and an OpenMPI compiler here. So we are doing srun here to launch this MPI job. You could also use MPI run. I have a different example for that. But one thing I should note is that right now we only support, actually we will only support MPI launch mechanisms that are integrated with the scheduler. This is because on a shared node, if we do an SSH based thing, it could get real complicated. So remember that you have to go through the scheduler either way, either if it's an srun or an MPI run that's integrated. So the one other thing is basically, so let's look at an OpenMP job and then I'll talk about this piece. So you can do partition equals shared, nodes equals 1, and task per node 1, and CPUs per task 16. Now here I should caution, this is again different from Comet. So on Comet, you could have done n task per node is 16 and then launched an OpenMP job and it would pick up the 16 cores. But on Expanse, you probably will end up bound to 1 core if you do that. So explicitly ask for what you need. So in this case, we're saying this is an OpenMP job. It's going to have one primary task, and then it will spawn 16 threads. So what we are saying is do n task per node is 1, oops, and CPUs per task is 16. And then I'm basically doing a similar thing, setting up the environment, and then setting the OpenMP threads to 16 that matches the CPUs per task, and then run the code. So for hybrid OpenMP and MPI jobs, I want to go back to that NPS 4 thing. So because as I mentioned, you're basically partitioning into 4 NUMA domains in there. And the memory is interleaved on the 2 channels there. So if you're doing hybrid jobs, it's important that you try to fit your jobs in a way that basically lays out the OpenMP tasks in the same NUMA domain and doesn't cross domains all over. So it's very important for hybrid jobs, essentially. And we are developing an IB run script, which should be available when machine goes into production. So you can use IB run with options so that this happens under the covers for you. But it's important to remember this if you're writing your own way of launching jobs or scripts that you're developing. So because it could make a pretty big performance difference if you cross NUMA domains in this architecture. So I have a couple of hybrid MPI, OpenMP examples. Let me take a quick look at the time, how we are doing. So I have till 12:15, right?
Correct.
Okay.
And
so
you're doing fine, I think.
Okay, yeah, I think we are doing okay. Okay, so this is an example of a hybrid case. So basically, you can see this is a shared partition job with 1 node and 2 tasks per node. And then I'd set CPUs per task is 16. So you'll have 2 MPI tasks and 16 threads on each of them. And so I do the export here. And I'm doing basically a pin domain on option with the Intel MPI, which lets you say that, hey, you have an OpenMP set up here with the compact pinning that we want to do. So that lets you kind of lay out the task the right way. Now you can do other things like spreading, and all the options are available and you can look at it. But what we've seen with codes on, at least the ones we have tested so far, is that it's good to align with the L3 cache that's being shared on the 4 cores. So if you can do your OpenMP thread so that the 4 of those threads are on one CCX, that will work well. This is another example, basically similar setup, but now I'm using OpenMPI, so I'm doing a different thing. And here you can see I'm doing a map by L3 cache option there. So the next thing I want to look at is GPU nodes. And then compare it to what we were doing on Comet. So the partition is GPU shared, which was similar to what we had on Comet. And I'm doing a nodes equals 1 and tasks per node equals 1, the count, and all that's okay. The difference here is now I'm doing a dash GPUs equals 1, which is different from Comet, where you would have done dash gress equals GPU colon 1. And I'll talk about the multi-node thing where the difference shows up. So in this case, this was a OpenACC job on the GPU node. So I'm purging everything, loading PGI, which has the OpenACC support, and running the job. So the multi-node job is a little different again from Comet. So what you have is nodes equals 4 and task per node equals 4. In this case, I'm basically matching the number of tasks with the MPI with the number of GPUs. Not necessary to do this, and just as an example, with CPUs per task set to 10. So you have 40 total cores on the node. And then I'm basically setting the dash GPUs equals 16. So this is different, right? We are not setting something equals 4 like you would have done on Comet, where it was a per node basis. Here, this is the total number of GPUs. So you're requesting there. And then the rest of it is similar. You can use srun to launch an MPI job. So the last piece I want to kind of go into is the file systems. So when you log in, you're on your home file system. Basically, $home will also get you there. The home directory is limited in space. Like I said, it should only be used for like source code binaries and maybe small input files. You can have your job script here, but make sure that the job script is aware that it's not writing into the home directory, but writing into a Lustre or local scratch for the actual IO. You have a quota of 100 gigs on the home file system. And can't stress this enough, don't run any intensive IO2 from the home file system. This is not set up for high performance. So it's not the place for anything intensive. Like I said, you could have like simple, like, standard out kind of output go there. That should be okay. But if you have any parallel IO or, file per core IO that does large scale stuff, you should move to Lustre or local scratch. So talking of Lustre, so we have basically, that should be a singular there. It's a parallel 1 file system. So it's a global parallel file system with 12 petabytes, and it's available on all the nodes. There are 2 locations on this 1 file system. So it's important to remember it's a single file system. The Expanse Lustre Scratch $user, which we will purge for files older than 90 days based on create date. And the Lustre projects location, which is the Expanse Lustre projects group ID $user. So what we are doing here is, since it's the same file system, we set a user-based quota for basically the whole file system. and then track the group usage in the projects directory, and we'll basically follow up if someone's over limit. And the other thing to keep in mind is we are limiting the number, and this is true on Comet too. So we are limiting the inodes to 2 million per user. And this limit is basically in place because if you're writing millions of files, Lustre is probably not the right location for it, and you should look into changing the workflow to using the NVMe that's sitting on the files on each node. And if your workflow does need intensive, extensive small block I/O, or like lots of small files, you should contact us if you need help with using the local scratch. I mean, this particular Lustre file system has metadata on MDT and can handle a lot more IOPS, so it's a little more better equipped to deal with the small file I/O, but we still recommend using NVMe wherever you can. So that brings me to the node local NVMe based Scratch file system. All the Expanse nodes have NVMe based local Scratch storage. The disk size is vary based on the nodes. That's a typo there. Okay. So the regular compute nodes have a 1 terabyte disk. It's about 900 gigs usable. The large memory nodes have 3.2 terabytes of local disk and about 2.9 terabytes usable. The GPU nodes have 1.6 terabytes of local storage, about 1.4 terabytes usable. This is excellent for like IOPS intensive workloads. It's also pretty good in performance with large files too, as long as they fit in the storage that is there. So if you have codes that generate a lot of files on a per task basis, for example, OpenFOAM used to do that. I think the newer versions don't, but the older versions of OpenFOAM would generate a file per core per variable, I think. So for something like that, I would say you should modify things so that you use the local storage and only store like large tar files in the Lustre location. And just like on Comet, this directory gets created when your job starts. So it's in the prologue that job specific directory gets created. So it's a /scratch $user. Little different from Comet. It's job underscore the job ID instead of just the job ID on Comet. Key thing is this location is purged at the end of a job. So if you have any important data, that has to be copied out. And make sure if you're copying out and it's a million files, you're not copying out million files. You're tarring up that million files on the NVMe and moving the tar file to the Lustre. Or you can tar directly into Lustre, but don't try to move a million files into Lustre. That's going to probably not finish in the time that you have and will cause problems on the system side. So this is an example. Basically, it's a Gaussian application that has a Scratch directory setting. So you can see how we've used it. It's pretty simple. You just do, you point your Scratch directory to /scratch $user job underscore slum underscore job ID. The other thing to keep in mind is the /temp is not that large on these nodes. So if you are anticipating, if you're using code that just keys off the temp directory and writes to the temp directory, please set your temp dir, tmp dir variable to this location so that you pick up the NVMe scratch. So I think I'm about 5 minutes out, so let me summarize. So basically, we are using Slum just like Comet. All the jobs have to go through the scheduler, don't run on the login nodes. We support both node exclusive and shared partition, just like Comet. So you have a few extra ones to help you on the GPU side and also with the preempt options. The account information is required in job scripts. I want to add one more here. You should put in memory requirements explicitly also. And then we looked at the file system options. As I mentioned, we are going in production soon, so you will all get on and try this once the machine's available in production. Thanks. So let me stop and see if there were any unanswered questions on the.
I think the last question from Don is where you can pick up.
Let's see.
Can you say something about dev shem and the size and speed?
Let's see. Well, the speed's going to be a lot faster because it's 3.2 gigahertz memory. So the SHM should do better, hopefully. There are more channels per node also. Like so, let's see. The Expanse node does about, Marty, correct me if I'm wrong, but it's like 350 gigabytes per second, right? On the 325 gigabytes per second on the memory bandwidth total on the node, I think, compared to about 100, about 110 on Comet. So there's a big increase. Now, if you're in a shared partition, you're sharing that with everybody. So you could end up with a lower bandwidth per core. So it really depends on what's going on if you're in a shared node. But on a regular compute node, if you take the whole node, yeah, you have a lot more memory bandwidth per core. In terms of size, well, it's a 256 gigabyte RAM, so you will have to work with that constraint in addition to what your code needs. Let's see. Marty, was there anything else missing?
I don't think so. I don't think I missed any other ones.
Okay. So,
but yeah, and if anyone has, there's one from Kenneth.
So is there a way to signal to the job? I think maybe the question for Trevor. I'll have to check on that. There should be, I'm assuming.
I think I can. If maybe Trevor's muted, but so Kenneth, I think we've discussed this with the systems group, and so it's possible. I think it's just a matter of how much time we can provide to allow the signaling to actually happen and for you to catch it. So it's sort of an open question, I think.
So this is Trevor. I don't see the question in the queue, but is the question about a signal for preempting?
Yeah, kind of like
so there is the ability for the user to submit their job and ask for a specific signal to be sent when the job is going to be preempted. But there are limits to how early that can happen before preempt time occurs, because the preempt grace time is only 5 minutes. So you can't ask for a 10-minute notification because we only know in Slurm that it's 5 minutes until preempt time. So you have to look at the settings on that and figure out whether or not you can basically do all your work that you need to do to checkpoint your job within the time limit that you have. You basically think of it as probably about 3 minutes of time limit from that signal until you could just have the node disappear under your feet. So yeah, but you can definitely register your job when you submit it to receive a signal if it's going to be preempted. And that will come as soon as Slurm decides it wants that node. And then you'll get some subsequent signals again later on. But yeah, that's totally doable. That said, I don't think many people are using preempt right now, and it probably aren't even using that feature because the users that are using preempt in early user don't really care if the node disappears. They've got workflow managers that deal with all that kind of stuff. So,
hey folks, thanks Trevor. I'm going to step in. We're starting our 10-minute break now, although people are free to keep chatting if they want and asking questions. And we'll come back at 12:25, where Marty Candace is going to talk about modules compiling and basic optimization for CPU and then GPU. So that will go until about 1:25. So we're on our break, but like I said, feel free to keep asking questions or answering them if you want to. Thanks.
So one quick addition to answer Don's question about the dev SHM. So apparently the The SHM is set to half of the total memory, so 128 gigs.
Okay, thanks, Mahidar. I'm going to go ahead and pause the recording and we'll take a 10-minute break, stand up, do some stretching, and we'll see you back again at about 12:25.
I have a couple comments then.
Okay, I've started the recording.
Okay, everybody, welcome back. It's about 12:25, and we're going to go into our section on compiling and basic optimization in modules by Marty Candace. 2 comments. We typically post the chats, so we'll have those online in a few days, along with some interactive videos. And also the talks will be posted on a repository, and I posted the link into the chat, and we'll repost it at the end of the talks. With that, I'll welcome Marty Candace, and he can get started.
All right, thanks, Mary. Let me go ahead and share my screen. And let me talk. How do I go to full screen here? Forget. Sorry, 1 second here. Where is the view? Well, we can go ahead and get started. I'll figure this out in a second. So thanks for attending today. I'm Marty Candace. I work with under Mahidar in the user services group, and today wanted to go over what the module environment on Expanse looks like and how it's different from Comet. Apologize in advance that I have not completely fleshed out all the material for the talk today. So I'll go over some of the material regarding what the module environment does for you and how it's useful, and sort of give you some best practices of how to use it. Because in my experience, some users are a little inexperienced with setting up their environment, and it can kind of give them a bit of a headache. And so I kind of want to go over some sort of basic material that you can, if you're not familiar with what the module environment's doing, it'll give you some better context of why we're suggesting you use it in a certain way, and how to go about compiling code and then also running code as well. So, so I'll go over the module environment material, and then sort of use the second half of the talk to do some interactive demos and show you how, in real time, how you can, take, say, some code that you've compiled on Comet, if you have certain, if you've documented sort of your build process there, and how you can, modify it to then compile your code on Expanse, and how the different sets of software stacks that Mahi talked about are presented to you in the module environment itself. So let me close this chat so I can pay attention to the slides here. So I want to start with some basic definitions, though, for people who might not be familiar. So when you log into Expanse or Comet, right, the program that's actually running when you log into your terminal is the shell program, right? And so this is the fundamental interface that you use to interact with the system, right? So every time you log in, this shell program is running, and this is what you use to issue commands to the system to get your work done, right? And so the common ones, common Linux shells, are sort of listed here. The default when you log into Expanse will be your bash shell, and this is what's used by, I would say, majority of users on the system. However, if you do have a preference on what your default shell would be, then you need to contact us via the ticketing system with a change request. Essentially, this default needs to be set on the system side for each user. Okay. So when you log in and your shell starts up, you have a bunch of built-in commands that you're probably familiar with, right? So you have sort of the CD command to change directories, the make directory to create directories, the list command, the ls command to list the files and directories in your home directory or whatever directory that you're working in, right? So this is probably pretty basic stuff that everybody's familiar with, but there is a point that I'll get to here in a second. And when you are working on Expanse or Comet, many people often have multiple terminal windows open up, and these are both, for example, I'm running 2 different terminal windows here on my local desktop in this image, where these different shell sessions are individual instances of the shell program running that has its own, each one has its own state and environment that is set, right? So although these 2 windows look completely the same, right? There might be differences between the 2 shell environments depending on what commands you've issued in them, right? Now, there are when you're working with the shell, you can also set variables with the shell, and so basically a shell variable is just a string that you can attach a value to, and they can have different types. I'll show some examples during the compilation of using shell and environment variables when compiling code. But most importantly, one of the things that's a shell variable is only sort of bound to that shell session. So if you have, for example, in the last image, 2 separate shell windows open, and you've defined a variable in one and not in the other, while you're sort of maybe doing some deep interactive debugging or compiling your code, those environments might be different. So the shell variables are only local to a specific instance of your shell that's running, right? And so, for example, one of the things that shell environments are usually used for is for very temporary data that might change pretty quickly. And so one example of this is the present working directory environment variable. And so, for example, I'm showing here a bit of code at the bottom where I'm just echoing. I'm logged into Expanse. I'm echoing the present working directory. And when you log in, your default directory is your home directory on the system. But for example, if I then change to the Expanse Lester Scratch directory for my username, then the present working directory changes to that, right? These variables are used to track the changes that are going on of where you are on the system, and so that the shell knows when you run an ls command, what directory you want to run the ls command on, right? So this is pretty basic stuff, but just to give you some context, that this is what some of these definitions that you should be aware of. Now, environment variables are sort of the key to what the module environment is going to be controlling for you. And environment variables are just shell variables that are sort of exported to what we call the shell's environment. And this allows other processes or commands that you are running through the shell program to see these environment variables. So unlike just straight shell variables, the shell variables are only visible to the shell program itself. Environment variables are then visible to the other, applications, binaries, other commands that you might be running from the shell too, right? And so effectively, also one of the main uses is the environment variables are used to sort of configure how your shell responds to the commands that you issue. And I would say in general, environment variables are, unlike regular shell variables, environment variables are used to store more persistent data that isn't going to change much during your shell session. Okay, so for example, I'm giving the quick example here at the bottom of your home directory, right? No matter where you are on the system or whatever program you're running, you're probably going to want to know where your home directory is on the system. So this is sort of a static environment variable that really shouldn't change ever for you, right? Now, when the shell starts up there and you log into the system, when you log into the system, the shell undergoes this sort of initialization phase on startup, right? And it's usually a multi-step process that actually there's some configuration files that some of you are probably familiar with that are looked at by the shell and used to configure your environment. at startup, right? So there's going to be a default set of environment variables and shell variables that are in your shell's environment when you start up. And I won't probably go through all of the different initialization files that you can use, but I'll cover kind of the high level ones that we are most commonly used by people. So there's, I think I have a list of 7 in the next 2 slides, but there are system-wide shell initialization files, and these are the ones in the etc directory, so etc profile and etc bash rc. So these are launched basically by the operating, or the shell looks for these configuration files first. These are sort of system-wide settings that we control for you, and may put things in there from time to time to simplify sort of your default environment on the system. Now, you can also control what your particular shell environment looks like by modifying some of these other configuration files, or creating these configuration files in your home directory on the system. So the 2 most common ones that people would modify is either the .bash profile. These are obviously for the bash shell. The names are different for different shells, but the .bash profile is one. And the .bash rc is probably the most common one that I think I see users use on Comet and systems in general. So the thing about the reason there's so many different configuration files is there are different types of shells when you're running on the system, essentially, right? So this bash rc, you can see the description here, is executed when a non-interactive bash shell starts. And so, for example, when running a batch job script on Expanse. So this is why this one's pretty important. So if you modify your bash rc file to change sort of the configuration of your shell's environment, this is always going to be run for any batch job that you run on Expanse. And so this is why I kind of wanted to go over this sort of set of definitions and provide the context. If you try to modify your module, modify your environment through these configuration files, you have to be aware of when they're going to be executed. We see a lot of times people modifying their bash rc file and getting into trouble when, for example, they take, they're doing one type of workflow for a certain set of calculations or simulations, and then they switch to a different code, a different application for a completely different set of work, maybe some post-processing step, but they haven't changed how their bash rc was set up for the first workflow for how it needs to change for the second workflow. Okay, and so even though I'm going over this material, the key takeaway is really to not use these configuration files. This is what the module environment on HPC systems is for. It's going to allow you to easily modify your shell environment on the fly for each individual job type you might want to run on the system. Okay, and this is sort of a little bit more information. I didn't quite change the title of these slides, but this is, as I mentioned, there's different types of shells, and when the different configuration files are executed depend upon whether it's a non-login or login shell or an interactive versus non-interactive shell. And so I'll clean up these notes for you online, but I don't think we necessarily need to go into it unless there's questions. But the key one is for when you're running a batch job script or a bash or a shell script in general, is a shell script is always running in a non-interactive shell, right? And that's why this modifications to your bash rc will affect any script that you run on the system, right? And that's why the key takeaway is if you're going to run multiple applications with that require different environments on the system, you really don't want to modify your bash rc. Otherwise, you're going to have to change it for every single job that you need to slightly change the software environment around it, right? And so that's sort of my overall I guess, perspective on the issues I see with users using their bash rc. Now, the module environment, you'll see, is mostly modifying both environment variables that are required for a certain piece of software, but the two most important things that it's modifying is your path environment variable. So if you're not familiar with the path environment variable, right, this is what is allowing, when you run a command in your shell, in your terminal, right, the operating system needs to know where to look for that command. So if you've compiled your application and you have the binary sitting in some directory in your home directory, if you haven't told the shell program about where to look for that binary, it won't be found. You can't just run the command and expect the operating system to know where the binary is, right? And this is the same issue with any command that you're going to run from the shell, right? And so the module environment, one of its main purposes is to control these path changes for you, so that when you load a module, it tells the shell where to look for the application and all of the dependencies that are required to be available in the path for you. And this is probably the second most modified variable that you'll see that the module environment is doing for you. So the LD library path, if you're not familiar, is basically where the shell is going to look for when you go to run an application. If it's compiled against, say, shared libraries, again, just like the operating system needs to know where to look for the binaries, it needs to also look for the libraries that it's going to call out to, right? And so it's, again, this is what the module environment is actually doing for you under the hood. It's trying to simplify all of these path changes to set up the shell environment to, as easily as possible to get you, a simplified user interface to running the applications that you want, right? Now, on Comet, what we used was the environment module system. So this module system is one of the module systems that are out there that allow you to set up a nice command line driven interface to make all of these changes to your shell's environment, right? And it's particularly, many people who are familiar with running HPC systems or running on multiple HPC systems, you've probably used environment modules before. If you've run on Comet, this is the environment module system that we've been using there. And it's a little bit of an older version of what's been used before. But if you're curious about the details, right, there's the link to the URL for the project. And so the module environment gives you the module system essentially gives you a set of command line tools to navigate the software that's been installed on the system and is manageable by the module system itself. And so these are the module commands that, if you've used the module systems before, you're familiar with. These are probably the ones that I use the most that I just listed. So module list allows you to look at what modules are available or what modules are currently loaded on the system. Module avail can be run with or without this package input to look for what's available on the system. Module purge allows you to sort of clear any modules that you've loaded. And again, which is the next commands if you want to actually put a specific package into your shell environment, you do a module load. If you want to take it out, you do a module unload. And then a module show is basically to get more information about the package itself. For example, I'll show you that it tells you more information about how that application may have been compiled, for example. So I have examples in here, and they're kind of not useful. I might switch over to doing some interactive work before I get to the new module environment system. But let me go ahead and boot up a terminal here and log into Expanse. So let's just go over the module commands on Expanse, at least the ones that are going to be exactly the same as you ran on Comet. So for example, my first one in the list was a module list. Let me do this. And so when I log into Comet, or sorry, when I log into Expanse, you see here that there is, like on Comet, there is a default set of modules that are loaded for you. And so it's this shared module, this CPU 1.0 module, and this default module there. The only one you really need, is the CPU one, which we'll talk about in a second. But let me just go through the other commands. So I think the next one in my list was, let me just double check here. Oh, yeah, module avail. So for example, if you want to know what compilers are available on the system, for example, if you're interested in the GCC compiler, you can just run a module avail GCC, and it'll give you a list of all of the GCC compilers, or perhaps if GCC here in this example is shown in the name of the module name, it'll also appear here. So you can see here we have 4 different versions of GCC shown here, and 2 are actually the same version, and I'll explain that in a bit here. But then you can see if you just have GCC in the name that you're searching for, it'll also show other packages that might be there with GCC in the name. So for example, this looks like we have a netcdf and an OpenMP library that were compiled with GCC on the system. Okay, the next one was probably module purge on my list. Oops. Right, so if I have some default modules loaded, the module purge command will unload all of the modules that have been loaded for you, right? Oops. So now I have a clean environment that has none of the other environment variables that may have been set by those other modules in the shell session, right? And so let's go through a quick exercise and show you how the module environment is or how the module system is actually making changes to some of those environment variables that I mentioned, like path and LD path, right? And so if I do an echo, I can see my path and my LD library path, right, which has nothing right now. And so if I want to, say, compile code for say, the AMD compute nodes, what we've set up in the module environment is, maybe let's do maybe a module show while we're here. I don't know if Trevor's actually put a description on here, maybe, but yeah, he has. So it looks like this module CPU 1.0 is basically to load the software that has been compiled for the AMD compute nodes on Expanse explicitly. So this is kind of your meta module that you'll load to get access to all of the compilers, MPIs, math libraries that you should use for Expanse's AMD compute nodes. So let's go ahead and do that. So we'll go ahead and load CPU.1. And if you do a module avail, you can then see what packages are available. And so I think, as Mahidar mentioned in his last talk, we're using SPAC to build and deploy all of the packages on Comet for users. And so this is probably a good point to explain what's going on here with all of the modules that you can kind of see on my screen now. So the module load CPU 1.0 loaded all of the packages that were shown here in this CM shared apps SPAC CPU LMOD core set of packages. Okay, and you can see below it, though, there's also a bunch of other modules where the CPU 1.0 module lives, actually. And these other modules are essentially right now visible to you these are sort of standard modules that come with the system manager that we're using to sort of deploy all the system software. So we're actually, I think we're going to try to clean this up a bit, because essentially you don't need to look at these CM local, CM shared modules here that are sort of extraneous and should, for the most part, for example, this is where when I did the module load GCC or module avail GCC, we saw 2 versions of the GCC 920 compiler. So one was coming from the SPAC installed version, which you should use if you want to use GCC 9.2.0. But there's also another GCC 9.2 here in the CM local that you could use, but this is really for the system administrators at this point right now. And so hopefully we'll get this cleaned up so there's not too much confusion. However, I will mention that there are some modules that you will want to potentially use in the, say, CM local and in the CM shared module environments. There is obviously the CPU.1.0 and the GPU.1.0, which are these meta module files that we've created. You'll also, if you're using Singularity, Singularity is visible here in the CM local module environment. There's also in user share, we have, if you're using Globus, this is one that will likely stay in sort of the visible module shown to you. And then also, if you've looked at the Expanse, user guide, there's also if you want to check your accounting and allocations, the SDSC.10 module file here will load sort of this Expanse client package that you can use to check your allocation usage, essentially. Right? So personally, I think it's still a little confusing for some people, but this is sort of, if you're if you're on the system now or on the system soon, you might still see some of these other modules, and just want to indicate not to get confused. If you're trying to compile your application for either the AMD compute nodes or the Intel-based NVIDIA GPU nodes, the 2 packages that you really want to focus on first loading is either the CPU 1.0 and then the GPU 1.0. Right? Okay, so you can see here that we have the CPU 1.0 module loaded. Now, if you want, I think as I mentioned to Ron in the chat earlier, if you want to compile for the AMD compute nodes, the GCC 10.2.0 is the compiler that you'll want to use. This is the one that will have the Zen 2 optimizations available. And I assume if you use, say, as Ron was asking about, the dash march equals native, it should hopefully pick that up, that these are AMD compute nodes and use Zen 2 nodes, and use that as the architecture to compile against. Right? So just kind of clean this up a bit. So as I said, right now we have just the CPU 1.0 module loaded. And what we're going to do now is module load GCC.10.2.0, and hopefully we'll see the path changes that have been made. And you can see now, prior to loading the GCC 10.2 module, the path and LB library path were different. And now if you want to just say run GCC, right, it's that version of GCC is the first GCC found in your path, and that's the one that is available in your shell session to compile code. Right? For example, if I do a module purge and then figure out which GCC, right, you'll see that you get the system GCC. So GCC 831 is the default GCC for basically CentOS 8. Right, and so this is why the module environment exists, to help you make changes to the path that you need to get access to the different versions of software. Okay, and so that is that's what the module environment is doing for you. And this is why if you have different applications and you're going to compile them in different ways and then run them, you really don't want to put the modules load commands in your bash RC file. You really want to put those commands in either, say, a build script, which we'll look at shortly, that you want to use to compile the code, or when you go run the code, right, those module loads have to be the same. So you actually want to just load the modules in your batch job script itself, right? Otherwise, you're going to probably run into some headaches if you forget to change your bash RC before you run a certain application, right? If you're switching from one workflow to the other, right? Okay. So maybe I'll stop here for a second and ask if there's any questions about anything that I haven't covered in the module environment. I think I just remembered one point that I definitely wanted to make, but maybe I'll stop here for if there's any questions. I don't know. Okay, I guess. Sorry, I don't see the chat, so.
Yeah, so Marty, there's been a lot of questions and Trevor and Mahi are doing a great job answering them. I don't think they've been stumped, so it's quite active.
Okay.
Great job.
Good. Okay. Okay, so we've sort of covered these basic module commands that you're probably familiar with on Comet. So I want to just highlight, before we switch over to actually showing some examples of building code on Expanse and interacting with the module environment to do that, and the changes that I would have to make to other other pieces of software that I've compiled before. The key thing that we need to point out is that the module environment, or the module system used on Expanse is different from Comet, right? So on Comet, we use the environment module system that I had a slide on before briefly, which is one version of a module system that you can use to manage all of these path changes and access to the software on an HPC system. LMOD is a newer system that was developed at TAC actually. So and one of the things it does nicely is it tries to help the users avoid mistakes that could be made with the environment module system that was available on Comet. And in particular, the way they do this is through a hierarchical module system, essentially, right? Where essentially, if you want to compile a code with GCC 10.2, like we just showed, and it's an MPI code, you need to then load an MPI module. However, on Comet, you could load a compiler module, one version of a compiler module, and an MPI module that weren't compatible necessarily, right? So usually what we do on these HPC systems is we cross-compile, we compile multiple versions of the MPI for a particular compiler, right? So if you really do want to have access to OpenMP, Intel MPI, and MVAPage2, you really have to compile a version of each of those for each compiler that's available on the system, right? But the one problem with the modules environment, if you didn't have all that, all of those different versions available for a particular compiler that you wanted to use, you could get caught up by loading a compiler module that did not have a compatible version of, say, that version of MPI that you wanted to use, right? And you'd probably send us tickets like, why can't I get this to compiler? Why isn't this running? Also, for example, one of the common problems we would see is users would load multiple versions of MPI in their bash RC, or actually in their batch job scripts, and that would then confuse your application of which MPI to use. And so LMOD allows uses this hierarchical system to avoid these types of problems, where you can only load the types of MPI that are available for that particular compiler, right? And so this is kind of what's nice about LMOD is it helps avoid these types of problems that you might have run into in the past on Comet. Now, the one I would say, the one thing that is going to be less familiar to you is how that happens, like in practice. Maybe I think a lot of people have probably used LMOD on different systems, so they are probably familiar with it. But I'll just go ahead and show you what this sort of means in practice. Open up my terminal again. Okay, so let's go ahead and clear and so what do I have loaded? I have no modules loaded in this shell. So let's go ahead and load. Let me go ahead and do this, right? So if we do a module, so if we start with a clear module environment, right? And you do a module avail, right? You'll see that there is no SPAC modules anymore. It's just those default modules from the cluster management software that I mentioned before, right? And so that's why these sort of meta packages exist in the management modules, essentially, right? So if you load CPU1, that's what gives you access to the SPAC-based installed modules, essentially, right? And so let's go ahead and load. So we see the meta packages load the correct SPAC environment that you want for either the CPU or GPU nodes, depending on what you want to do. And then let's say we want to build an application with GCC 10.2. So if we do a module load GCC 10.2 and do a module avail, you'll then see that there is another sort of sub-module environment here that was created with all these packages. That these packages were built with GCC 10.2, right? And so if you, as you can see, we have, a fair amount already of different applications in here, because this, as I mentioned, GCC 10.2 is the one that has the Zen 2 optimizations that you can take advantage of. But again, we also have multiple versions of MPI, like I mentioned. But what's nice, like I said, about the LMOD system is you're only presented here the certain types of MPIs or math libraries that are associated with and compatible with GCC 10.2, right? And so let's go ahead and say this is an application, say it's an MPI application that I want to build, and I want to use, let's say, OpenMPI. Right? And do a module avail. And then there is another sort of nested environment shown here. Once you load a certain version of MPI, you'll then discover that there are already certain applications that were built here with both GCC 10.2 and this version of OpenMPI, right? And so as you progressively load, say, your compiler and then your MPI, you'll be revealed more and more applications that are available to you from that combination of compiler and MPI. So for example, if your code required FFTW, right, this one is presumably compiled for using the parallel options to use MPI, and it's compatible with the GCC 10.2 and OpenMPI 4.04. Right now, one of the questions you'll probably have if you're not familiar with LMOD is, okay, yeah, this is great. I can it sort of helps keep the module environment a little bit more organized and prevents sort of conflicting modules from being loaded at the same time. But how am I supposed to know that that version of FFTW is available with, GCC 10.2, OpenMPI 4.04? Like, is it like, for example, your question might be, is it available for MVAPIC 2 yet? Like, how do I know? And so one of the new commands that you'll probably get familiar with is module spider. And so this is one of the new module commands that isn't available in the old environment module system. This allows you to search essentially this hierarchical structure for the packages you need to load to get to the packages you want. So let's go ahead and run that example that I just mentioned of FFTW, right? Like if I wanted to use a different version of MPI or compilers, what FFTWs have been compiled and are available for the different combinations that I might want to use, right? And so if I clear this and do a module spider FFTW, you'll see a list of the different modules that are available, FFTW modules that are available, and what modules you have to successively load to get to it, right? And so you can see here, if on the AMD compute nodes, we have an FFTW, a serialized version, I'm guessing that's what this is, compiled with only GCC 10.2. We also have parallel versions compiled with both MVAPICH2 and OpenMPI. Right? And so that's how this is the one new command that you need to really get familiar with if you're sort of confused about like, okay, what software is available? Because it's gonna, I mean, you don't want to just start loading random compilers and MPIs to figure out which, what sort of mass libraries or other dependencies you might need to build your software, right? And so this module spider command really simplifies the process of figuring out, it figures out for you, it's like, all right, what's available and what's already been compiled and like what combinations of other modules are needed to be loaded to use it, right? Okay, so I think that's the only really new command I wanted to cover in LMod, because it's going to be the one that you'll get the most bang for your buck right off the bat. Okay, so I'll stop here for a second, and if there's any questions, let me know. I will sort of get set up here for doing some compilation examples. So, I don't know if there's anything in the chat.
So Marty,
Yes.
just about now, you should be looking at GPUs. So when you're ready to move to GPU, I don't know how much you've allocated for each one. Just
I mean, I didn't really stick to the original plan of doing 2 separate ones. I wanted to really cover the module environment in general, and then I'll show both. Maybe I'll start with a GPU example.
It's up to you. I'm just letting you. Okay, that's fine.
Yeah. So, okay. So now that you're sort of familiar with the module environment and some of the differences that are on Expanse versus Comet, one of the things you might want to do is, take some code that you've had on Comet, built on Comet, and then transfer it over to Expanse. Now, I'm gonna pick some examples that I have from Comet right now and show you how I modify, or both show you how I compile code in general, and how you might want to think about doing something similar for sort of reproducibility aspects in the future, but also just how to then use the module environment that we just explored to compile code on Expanse. So the first thing I want to say, and I think Mahi mentioned during his talk, is unlike on Comet, where we sort of didn't monitor this as much as maybe the system administrators would have liked us to. We really do encourage you to compile code on the type of compute node that you're running on, especially if you're going to be using GPU code, right? The login nodes are AMD. They're very similar to the actual compute nodes out on the system. But even for CPU code, we do encourage you to say, if you want to do some sort of interactive compilation to figure out how to build the piece of software that you want to to grab an interactive session and do that and sort of develop that build process. And in particular on the GPU sides, you really should do that because, again, as depending on how you sort of structured your build process, right? If you're using, say, the MArch native kind of settings, right, you need the compiler to pick up on those optimizations, and you need to sort of, if you want it to be simpler, you need to really be on the type of architecture that you're trying to compile against. you can cross compile, but we've run into problems ourselves with that a bit. So this is why we're really encouraging you to compile on the node type you want, and try not to do it on the login nodes, because sometimes compilation processes can be a bit involved and computationally intensive, and that would affect other users on the login nodes. Okay, so let's go ahead and grab an interactive session. I think I'll do the GPU. I'll do a GPU example. Just grab the commands. And I guess I'll do, let's see, 16 gigabytes, 1 GPU. And I'm sure I have less than 30 minutes, so I'll just do this. Oops. So this is, again, Slurm is not loaded in your default environment. So okay. So I basically started an interactive session on one of Expanse's GPU nodes, and now I didn't set this up real quick. Okay, sorry, I need to correct this real. Sorry, I need to log in with my credentials correctly. So I can pull some files from Comet. Okay, so we're on an interactive compute node, and I want to pull some files from Comet. This is not working right now. Oh, it's probably not. Sorry. Let me just do it here first. Okay, so I'm going to install some software in my software directory here. So I have some software sitting on Comet. And some build scripts that I've used in the past. Okay, so I'm going to grab these. I'm going to get this build script. Okay. So GROMACS is a molecular dynamics code that's widely used on Comet. And so from time to time, we've had to sort of build multiple versions for people when we don't really have those in the standard module environment. So I have this build script that I've created to compile GROMACS with MPI, OpenMP, and CUDA itself. And so this will be a good example because there is a slight difference with the CUDA. Okay, so let me go open up this build script. So this is what I do when I'm compiling code. So you might be working interactively for a while to figure out how to build software, but eventually once you sort of have the set of modules that you're using for your application and the different dependencies that are needed and how you sort of configure that, what I do is I create a build script essentially that sort of codifies all the changes that I made to the environment itself to compile the code. And the reason I do this is because usually I'm handing these build scripts to users so they compile this version of the code in their home directory. But as I mentioned, you also have to load those same modules when you run the code, right? And so by having a build script like this, which could also be run as a batch job, you can see here I have it. So I can compile the code in batch form as well. I don't have to do it interactively. I can just launch it and forget about it and let it compile and then come back later. but it really codifies what was done to compile the code, because you need to know exactly what modules were loaded when you compiled the code to then run it, right? And so this is where another common problem that users get tripped up on. They forget how they compiled the code, and then we have to sort out what modules there need to be loaded when they try to run it, right? And so that's why, you know, trying to codify things in a build script like this is I think, a good practice. And it helps us when you run into problems, so we can actually see, you know, oh, this is what I did and this is where it's failing. Can you help me figure out why this part of the build is failing? So this gives us a more complete view of what you were actually doing. Okay, so let me try to maybe reduce the text here a bit of this build script. What time does this session go to, Mary? Can you just remind me? I think is it 25?
Yes. Yes.
Okay, great. Okay. So I'm just going to log into Expanse here. And just so we can have another screen here for the what modules I might want to load, right? So again, by default, when you log in, right, the CPU stack is visible to you, right? And so what you'll want to do if you're compiling on GPU is do a module purge and then module load GCC 8, module, sorry, GPU. I'm getting ahead of myself, right? You can see that the path and the module environment for SPAC is different than the one on the AMD compute nodes, which makes sense because this is these are Intel-based CPUs and NVIDIA GPUs. And you'll also notice there isn't, for example, a default GCC and the module that's loaded in the SPAC environment up here. And the reason for this is we're actually using the system GCC 831, right? That's already in your path for most of the builds that we're doing on the Intel compute nodes. So that's what I'm going to use right now. And so in this case, I don't really have a module that I'm loading for the compiler itself, because basically all of the defaults here are being built with this GCC 831 that's available. So for example, this OpenMPI 404 is being built with GCC 831. So this is one caveat to the module environment on the GPU side. Like, you have to sort of keep in your head that these packages in this SPAC environment were built with GCC 831. So if you want to use this OpenMPI 404, you're going to, you're by default, you're using the GCC 831. So I'm going to change my build script here to use that OpenMPI 404. And let's just double check to make sure that if I do a module load, there's also a CMake in there. Probably doesn't matter. Well, there's a CMake here. It's already there. So I'm going to change my CMake module here to the 3.18.2. And then this is where the caveat comes in with the module environment on one of the caveats on the GPU side come in. So right now, at least, the CUDA modules that are available are actually in the system managed module environment. And so if we look at this, you'll see the CUDA 10.2 is available down here in these CM shared modules, right? And so the default one to load, I believe, is just the toolkit. And I don't think I've run into any problems with having to actually load the rest of them, but you might run into issues like that. And if you do, let us know. But I believe everything that I've done testing wise, if I just use the main toolkit one, it works. So But that's obviously dependent on the codes and that you might be compiling against. I mean, basically, again, remember the modules are just telling the shell to really know where to look for certain things. So if all the paths that are in the toolkit module are there and really point to most of the libraries in CUDA that you're compiling against, it's probably fine. But you might run into some edge cases that we haven't come up with yet. And in this case, maybe I'll change this. I know the GrowMax is a new version here. And essentially, this is what my build scripts look like. I sort of declare some environment variables that set what modules I want so I can use them later to describe where to install things and create paths and things like that. And essentially, right, there's no, one caveat here is there isn't really a compiler module. It'll just be GCC by default. But you then, I always do a module purge before compiling. And then I load the modules that are needed to create the environment that I want to then compile the program, right? And then I do here, I'm just downloading the source code, creating some directories, and then running CMake, which is the build the build program used for GrowMax here. And there's different settings that you can set for obviously for your code, and these are sort of just default ones we've used on Comet forever. And so all I've really done is change the modules that have been loaded, right? And then I can either run this interactively and start compiling the code. There was an error here. What was that?
Marty,
Oh,
you're missing
I forgot.
the GPU.
Yeah. So yeah, I actually did this earlier when I was testing the examples. So yeah, I did it again. Okay. So there's the one other module that I need to add, which Mahi just pointed out, is Expanse and GPU module, right? Right, because basically when I do the module purge, I've removed the GPU stack from my environment, right? And so if I do a module load, that should then load all of the packages that I'm expecting to see, and then I can load those subsequently, right? So yeah, so that's what we usually do when we're trying to help you compile software. Is we construct these build scripts that sort of cement in what was done. And so I definitely recommend trying to do that. I mean, obviously, sometimes you want to do this interactively and just get a sense of like, oh, is this going to work? Is this going to work? Which is fine. But as you work through it, I would definitely recommend having another terminal open with creating that build script on the fly. Because for example, in this case, I was very easily able to switch over to GrowMax, say 20 from 19, what did I have, .4.3 to 20.4, and basically changed nothing other than a few variables that were in the script, right? I just changed the variables that were pointing to different module names and the version of the package itself, right? And so not every code is set up to do that easily, but it's a good practice that I would encourage folks to take a look at. And in particular, as I've set up the code, I'll just stop the compilation now. You can also set these up as batch job scripts, because for example, there was someone who asked, well, if I'm doing this in debug and it's going to take longer to compile my package, how should I do that? You could either wait for an interactive node on one of the regular compute nodes or the regular GPU nodes, or you could also, if you have a build script like this, you could just submit it as a job. Like once you know that the build is looking like it's going to work, you can submit it as a job to the scheduler itself. And one thing that's nice about that when I'm compiling software is that you get a build out. I mean, you have the complete output file from the build itself. So even if the build fails, you know where it fails, and you can look up the entire history of the build to see what was happening, right? And so if you want, this is what we do when we're compiling code, and it's really helpful for debugging purposes. And it's another reason that I definitely would encourage you to think about building code this way, and especially since we're sort of asking people to try to build out on the cluster itself, not on the login nodes. This is one other way to do that. And I think that's about out of time. And if there's any questions, I guess we should take them now. And I think there's probably a break, so I can stick around during the break if people have questions.
Hey, Marty, I
Yes.
got pulled away for a couple minutes in the middle. I don't know if you already mentioned this, but do you have examples of these Slurm batch compiler build scripts in the examples area for people to kind of take what you've shown very quickly here and implement it themselves?
Yeah, no, that's a good question. No, we do not. I do not have them on. I can put them on today, but yeah, we do have some of these sitting on Comet, but yeah, they're hard to find. Essentially, this is yeah, maybe we should keep yeah. Basically, yeah, we'll put these somewhere. Some of these examples in on Expanse in the examples directories that we have. I don't know if anyone from our team has put any examples on there yet, but I think by the time we get in production, we'll definitely have some examples there. So, and if you're currently on the system in terms of early user program, you know, if you want access to some of these examples, I can, you know, ping us with a ticket and I can show you where they are on Comet and you can sort of play around with them. Or, you know, copy one over essentially.
Okay, well, if there's no more questions, thanks, Marty. We'll come back at 1:35, where Nicole Wolter will talk about job charging, followed by Suba. She'll go over the Expanse portal, and then we'll do interactive computing. And we'll see you guys in about 10 minutes, 1:35. Going so we stay on time. We have Nicole Wolter, who will be talking about job charging, followed by Suba, who will talk about the OOD portal, and then I'll talk about interactive computing. This will run till 2:15, and then we'll have a final session on data management. Okay, thanks.
All right. So can everyone see my screen? Or
Yeah, looks good.
I assume you can all see my screen. So I'm going to talk about Expanse, managing allocations and charging. And we've touched on this a little bit in the previous presentations, and there was a lot of discussion in the chat about this. So so some of this might be repetitive, but there are some little tidbits in here that are going to be different for Comet and that we haven't touched on yet. So I hope it's helpful. And one of the goals that we can get out of this presentation is that based on how we charge and understanding how we charge, you can better prepare your proposals, because you know how the resources are going to be used and how you can use them. And it'll also help you when you're thinking about how to set up your workflows. So I'm going to start with the upbeat that job charging is super simple. At least on the user's behalf. You can talk to our system support staff and they'll say they work very hard to make sure that it's super simple for you all. So on the top level, as Mahi mentioned before, Expanse and Expanse GPU are completely separate resources. And at SDSC and Expanse at Exceed for that matter, all resources are allocated in what we call service units or SUs. But just because they're called the same thing does not mean that they are the same at all. So as before with the Expanse and Expanse GPU, an Expanse unit is allocated in core hour, where a GPU, Expanse GPU SU is going to be a GPU hour or a GPU hour. In addition, you need to know that even if they are both allocated as core hours, where Expanse and Comet were both allocated as core hours, the Expanse core hour is not equivalent to the compute or the Comet compute hour or core hour. Sorry about that. Some of the things another thing that we need to take into consideration is when you request a job, you're not just requesting the core hour, but the core hour is represents a core hour. So with the core hour, you are also considering what else comes with that. So that'll include the memory, or for GPUs, it'll represent the cores and the memory involved. Kind of the high level thought here is that jobs are charged for the resources that you request. And when I say resources you request, I mean the actual cores or GPUs you request. And that'll be separate from, I'm sorry, the jobs charged are for the resources you request, not the resources that you use. So if you request 5 cores and you run it for an hour, but you run a serial job, you're going to get charged for all 5 cores regardless. Another important thing to note is that the minimum charge for all jobs is 1 SU. So if you run on 1 core for a couple of seconds, it's going to get charged 1 SU. But if you run on 1 core for an entire hour, that will also get charged 1 SU. So when you're thinking about your workflows here, it's something that you should consider into bundling lots of small jobs together in one job. So on the high level, the charging algorithm is going to be the resources you request, so either GPUs or core hours, times the job duration. The job duration is going to be the time in hours, times the charge factor. And the charge factor is going to represent or is going to be dependent on the partition. So Mahi talked about the partitions already. So as we know, we should be familiar with most of these. So we have 9 partitions out there, 7 of them. So the compute shared, GPU shared, large shared, debug, and GPU debug are all going to have a charge factor of 1. But with Expanse, we added these preempt and these preempt, the GPU preempt. And so these are discounted jobs that you can run on nodes that aren't previously allocated. But as discussed before, if another job comes into the queue and needs to use those, your job will be preempted. Couple things to keep in consideration. First, the good. In preempt queue, you can run for 7 days, which is significantly larger than you can run in any of the others. But on the flip side of that, there are no refunds regardless. And the other thing to note is that in preempt, it's like a compute or a GPU request. You'll be charged for the entire core or the entire node. So we allocate it in full nodes. So GPU charging, you can think of it kind of like a Tetris game. When we're scheduling, we're trying to fill in all those little spots. So there was some discussion before about if we allocate in node hours versus core hours. And one of the reasons we do core hours is because we feel that with the shared queue, we can fill in all those little back parts a little bit better. So again, part of the reason for having the preempt queue now is also that we can backfill in and fill in the empty spaces. So one Expanse node has 128 cores and 256 gigs of memory. This is different from Comet, where it has 24 cores and 128 gigs of memory. So when you take the fraction of the smallest unit that we can allocate, then is 1 Expanse SU or 1 core hour is going to be 1 core and up to 2 gigabytes of memory. Whereas on Comet, because we had fewer cores, even though we had less memory, per core you got a little bit more, you could get a little bit more memory. You could get up to 5 gigs of memory. Something that's really, really important to note at this point is that in all partitions, unless you specify memory, you're going to get a default of 1 gig of memory. That's across all the partitions. So again, if you just select, you just want to have, you're in shared and you want one core, by default, it's going to put in 1 gig. So the charge here is fairly straightforward. It's the equivalent of CPUs. So the equivalent of CPUs is going to be the number of cores or the memory that those cores have. So if you request 1 core and 3 gigabytes of memory, the 3 gigabytes of memory is going to be more than worth 1 core, which means you pop into 2 into 2 cores. So you're going to be charged the equivalent of 2 CPUs for that. The wall clock time, or the duration, is going to be in hours, and then the charge factor, of course, is related to the partition that you use. GPU is very similar. So just to it's the GPUs, the charging is going to be the exact same. But again, you need to note that one GPU on Expanse is different than what we had on Comet. On Comet, we actually had 2 different types of GPUs available. But on Expanse, one GPU node has 4 GPUs, 40 cores, and 384 gigabytes. So if you reduce, or you take the fraction that will be down to the lowest portion of that node, you can have up to one GPU, up to 10 cores, and up to 96 gigabytes of memory. So again, for GPUs, unless you specify differently, by default, if you request one GPU and don't add the other elements into your batch script, you're also only going to get 1 core and 1 gigabyte of memory. The equation here is similar: equivalent GPUs, job duration, charge factor. But again, the max is going to be out of GPUs, cores, or gigabytes of memory. So whichever has the most there is where it's going to fall in. So we talked a little about the, Marty actually mentioned about Expanse client tool we have. So the Expanse client tool replaces the tools we had on Comet, which was show accounts and project details. And what this tool will do for you, so basically, Marty also mentioned that to be able to run this command, you have to load the SDSC module. The syntax for this is Expanse client and then the command that comes behind it. The commands you can use are either users or projects. When you list projects, so when you use Expanse client project, you need to also specify the project that you want to view. This will show you who all is on the allocation, what has been used by each individual user, what the total is available to all the users. So in our account management system, we can actually specify percentage of allocation that's available or cap users at this. So that might be different depending. In the example I have here, it actually, everyone in this allocation has the same amount available to them. And the final is what everyone combined has used on the project. The other command that you can use is users. And user will show you specifically what you have access to. So Expanse module client user will show you all the allocations that you currently have available to you, and it will show you your usage. What's new with this tool is that we have a verbose option, which is really, really nice. So it doesn't only show you our accounting updates into the database nightly. So everything that's been run today, if you go into the Expanse portal, you will only see information for all the jobs that were run yesterday or before then. You won't see what happened today because the jobs are uploaded at midnight. But with this tool, the two at the bottom here where you can see used queue and used by project queue, this will show you what is currently in the queue, what is currently running, and what has been run today. So that actually reconciles quite frequently. So you can, if you request a job to run for 24 hours on 128 nodes, it will show one thing, but if it pops in and pops out and immediately fails, and so it just runs for a second and only gets charged 1 SU, that will drop down quickly for you. So I went really quick, and then I can give some more things, but just in kind of a review, the charges are based on the reserved resources that you reserve and you request, not how you're going to use it. The default is of 1 gigabyte of memory per core GPU in all partitions. So it's really important that you designate in your scripts the dash with dash dash mem. The minimum charge for any job is 1 SU. A thing to note is that we dropped the time limit from 10 seconds to 1 second. So any job that runs for a second will get charged. I wrote down here again the changes in the cores and what they are, and that we have new partitions. Some of the partitions in preempt, I think we're still considering how to best manage them and how to tweak them so that they are the most advantageous for our users. So I would recommend going to the user guide every once in a while, just in case we change anything. That's all I have. I went very quickly, and I know there's stuff I forgot. So why don't I open it up to questions? There
Hi,
are.
Nicole. Yeah, I think one of the questions that I was trying to answer just now in the chat was in terms of, maybe you can just review again the charging versus, say, cores and memories. Like, when are you charged more for one or the other?
So depending, so we can actually, we have a little more complicated equation for that, but basically the smallest unit that you can request for, I'll take the example of CPUs, is 1 core, and with that core you can use up to 2 gigabytes of memory. So if you request, you can request 5 cores and 2 gigabytes of memory, and in that case, the number of cores is more than the amount of memory that 5 cores would have. So you're going to be charged for the cores in that case. However, if you ask for 1 core and say 6 gigabytes of memory, 6 gigabytes of memory would actually correlate to 3 cores. So in that case, the memory is higher. So we're going to charge you for 3 cores in that aspect. Does that help at all?
Yeah, I think so. I mean, I think the question was, yeah, it's a matter of, essentially you have to think about the rule of thumb. I think I was saying in the chat was, you're going to be charged by the resource that you use more of over, say, the amount that's available on a per core basis. So as Nicole said, right, it's, if you want, for every core, there's effectively 2 gigabytes of memory available on the system. So if you need more than that for a single core job, you're going to be charged by the memory instead, because effectively you're taking that memory away from the other cores, essentially. So it's that's the general rule of thumb, I think, right?
Yeah. Well, and I should also add why we chose to set it at 1 gigabyte. So in a lot of cases, a lot of the applications don't need that much memory. However, some, in the case with the example I gave you of 1 core and 3 gigabytes, it makes more sense to take advantage of someone who's using a core and 1 gigabyte example. Again, this is the Tetris example. So we want to fill in that little slot. Instead of taking another core away from someone else that could be using it, we can use what's not being used, if that makes sense. I say,
Okay, if there are any more questions, yeah, thanks, Nicole. I think we're running a little long. So I think Suba is going to talk about the Expanse portal next.
Yes, and I can share my slides now.
Yes.
Okay, I can get started. Everyone can see my slides.
Yeah, looks good.
Okay. Hi, my name is Subha Sivanyanam. As Mahidar mentioned in his talk earlier today, we are developing a user portal for Expanse users. So this is a very short talk. I will just briefly describe the features of the portal and show a quick demo. So the goal of the Expanse user portal is to provide an integrated web-based environment for doing file management and job submission operations on Expanse using an easy-to-use interface. The portal is also being developed to serve as a gateway for launching interactive applications such as MATLAB and RStudio. So we did not build this, we're not building this portal from scratch. We are actually leveraging an existing NSF-funded project called Open On Demand, which some of you may have heard of. And we are just customizing the software for working with the Expanse system. So the portal provides graphical file management capability where users can view and operate on files in their home directory or on Luster Scratch directory. In addition to doing like basic file management operations like copying or moving, renaming and uploading files, users can now also edit files without needing a shell. There is a job composer area where users can create, edit, submit jobs, and also monitor jobs. We have provided some predefined templates that users can use, and they can customize it and submit jobs. We currently have example templates for jobs like MPI and OpenMP, and we'll be adding more. But however, if you don't see a job template that you think would be widely used for a specific application or for a research community, and you want that to be provided, please do let us know. The portal also allows the ability to submit an interactive job to the cluster. So, and without needing to install a local X server. And as I mentioned, we only have it for MATLAB and RStudio, but based on user requests, we may add more interactive applications. And for those users who need to access, who need a terminal, there is a integrated shell terminal with the portal, and that's very similar to many other tools that provide terminal access. So now who can use the Expanse portal is anyone, any PI or users who have a valid Expanse allocation and have the Exceed-based credentials. They can only access the Expanse portal. What that means is once your allocation is approved, and you need to have your home directory and everything set up on the back end before you could use the Expanse portal. And though this is obvious, any policy like scheduler, allocation, usage, security policies that's been set on Expanse resource, or any guidelines that has been established is automatically applicable when you're using the portal as well. So the portal is being developed and it'll go into production along with the cluster. However, we did develop a prototype for Comet that's available. If you're interested in checking it out, you can go to portal.comet.stsc, which is very similar to what we'll be providing for Expanse. So with that, I will quickly show a demo, and I have only about 10 minutes. Mary, is that right?
Yes, sorry, I was on mute.
So let me, so as I mentioned, you need to have Exceed portal username and password to log in. So you'll be automatically directed to the authentication page where you'll enter in your details, and then you'll be redirected to our portal. So once in the portal, you can see on the top navigation bar, it's pretty exploratory, but it's just you can access your files, or you can go for the job composer area. If you want the terminal, it's under the clusters, and you can use the interactive apps to launch your interactive job on the cluster. So I'll just show the my home directory. So this is my home directory on Expanse, and this is the graphical file management tool. And here I can view files, I can edit files, I can move and rename or create a new file in a directory. I can do all those operations here, and I can just show you, how just a basic edit. So this is my submit script, and I can, maybe I want to print out the date in addition to running this job. So I can do that, and if I save it, it gets saved. And then, I'm sorry, the Zoom bar, I can't see where the tab is. Have to go back. So as you can see now, the edits would be saved, and I can view the changes here, and I can submit this job using the job submission interface. So under the jobs, there's an active job and a job composer tabs. The active jobs is where once you have submitted a job, you can come here to monitor the status. If it's waiting in the queue, you can look at it, and you can also look at, essentially it gives you the output of S-control show job, and that's what it'll be listed over there. The job composer is where you would actually create your job scripts and submit it to the cluster. And if you're interested in using the templates, there is a template tab that you can access on the top or through the button. And right now we have a basic hello world. There's an MPI job, there's an OpenMP. And if you want to use any of these existing templates to start the work, you can just click on create new job, and that's created. And you can see the job script itself over here. And if you want to make any changes, right? So if you want to add your account information, if you want to modify the scripts, you can do so by opening the editor and saving it. And for the interest of time, let me just show you a job that has been completed. So this is a job that I ran yesterday. And as you can see, the output is just to print a hello world, and it did that. So in addition to creating and submitting job scripts, you can also run interactive jobs. And right now, I'll just show a quick example of you running a MATLAB job. Here you can choose your queue, the number of hours, what account you want to use, and where you want to launch the job from. And for this demo, I'll just launch it from my Luster Scratch directory. And I'm just running it for 1 hour. And once it's queued, it'll show up here. And you can launch multiple such interactive sessions. And you can, there is a tab where you can go view all your launched interactive sessions under my interactive session. Right now, the job is running. And for some reason, let's say you're debugging with a colleague, or you want them to see what you're doing, you can give them a view only shareable link. So they can also watch what you are doing. And so once if I launch the job, it opens up now it's failed to connect the server. Let me see. I'm sorry, I am not sure what's going on. I'll have to debug this one, but it will open up an interactive terminal where the MATLAB will be launched, and you can plot and display and open your MATLAB files and use the interactive application there. And if there is time, I will try to see what's going on, and I can even show this on Comet as well as how it's working. So other than that, if you're interested in using the terminal shell access, there is an integrated shell, and which you can use to log in, and you can just use that it's just a basic like a putty shell, and if you don't want to install putty, you can use this one. So this is the portal in a nutshell. We will be adding more features, such as where your information about your job and information about your allocations will also be displayed here. And we will also be adding more interactive applications as there is a demand. So with that, I'll end my talk and see if you have any questions.
So Subha, there was one in the chat about whether there's a REST API for OOD.
For OOD, no, we don't have a REST API for OOD for the portal.
Okay, thanks, Subha. So I'll go ahead and get started. And let's see if I can make this work. There we go. Does everybody see the talk?
Yep.
Okay. Go ahead and turn off my video. All right, so I'm going to talk about interactive computing, which is a subset of the user portal. So Subha just talked about the portal, and there's a lot of different definitions for interactive computing. So today I'll just talk about a couple of tools we're working with. And as Subha was saying, there'll be other interactive tools brought onto Expanse. So what's interactive computing? Basically, when I type on my keyboard and I interact with my computer, I'm doing interactive computing. But it's a little bit different as you gathered, and if you've worked on HPC systems, it's a little bit different when you're trying to do this on a high performance computer, and in particular on the compute nodes. You have to get them allocated, you have to get your hands on them, and you have to be able to work on them. So there's a lot of work being done in the field of interactive computing on HPC systems. There's actually an annual workshop that is being held. I think it's in conjunction with supercomputing on interactive HPC systems. So with that, here are some scenarios for HPC, interactive HPC, in MATLAB, parallel MATLAB, like Suba just showed you, and on Expanse, we want you to use it through the portal so it can be well maintained and you get better performance. There's Jupyter Notebooks, which I'll talk about today. And then there's Amazon has an application for some scientific application looking at airflow monitoring. So anytime you're running an application and you're accessing a cluster node, it's interactive HPC computing. So to get an interactive node, you have to run a particular command. So interactive nodes are particular nodes that when you get it, you'll be able to, you'll be logged onto it and you'll be able to run commands. That's where you can grab an interactive node and you can compile and debug code a little bit. We don't want you running your application on the login node, but if you need to do things on the command line, like your compiling takes a really long time, then you can do it on an interactive node. And in the future, there will be a full partition dedicated to interactive, but that's not up and running yet. So this is some of the arguments. I think you might have seen them earlier. The big change between Comet and Expanse is you have to give it the account information. And as Marty pointed out, the arguments to Slurm are a lot more exacting, so you have to give a little bit more information. These two work on the CPU and the GPU, and if you need help developing other interactive requests, let us know. And so I'm going to focus on Jupyter Notebooks and running them on Expanse. So Jupyter is an open source tool that there are two really popular applications. They're Jupyter Notebooks and Jupyter Lab, and they're actually considered services, and I'll show you why. And understanding that will help you realize a key aspect we're trying to focus on, which is the security of these notebooks. So we have a tutorial on running notebooks on Comet that will be ready for Expanse as well. So for more details, my talk kind of follows this very loosely. But go to that tutorial if you have questions. So normally, if you're going to run notebooks, you can run it on your laptop. And notebooks are popular in a lot of different scenarios, especially machine learning. You can run parallel notebooks. You need to use something like Spark. And there's a lot of applications that are using them. So Anaconda is great, but it's big and heavyweight. So we don't want to run that on an HPC node. So what we recommend is that you use the mini Anaconda environment called Conda. And so you can go to the tutorials and find out more detailed explanations, or go to the Conda site to install it. But the power of Conda installing it is it gives you your own local environment. So you can install the version of Python, like Marty was showing you with modules. It's very similar. It was originally created for Python. And so you can also develop your own Conda environments and then have different versions of Python in those environments. So it gives you a lot of flexibility and control for what you're doing. So we intentionally want people to use Conda, because that way we're not trying to keep different versions of Conda environments maintained for 10,000 users. The users will teach you to install Conda, make your own environment, and then you'll have a lot more control over how your applications are running. So you want to, you can also create these virtual environments. I won't do a demo of that, and you can look on the Conda site, but this is one way that you do it. You create the environment, you install the particular modules that you need, and off you go. To install Conda, we have long, full instructions on the tutorial, but it can take a long time. Just a warning, it takes a long time to install all that software. If you want to use Jupyter Notebooks, you need to install the notebooks and you need to install Jupyter Lab. It's pretty straightforward, but again, it can take 5-10 minutes for these to install. And then you want to make sure that the environment is working. A key issue that we're addressing at SDSC is the security of Jupyter Notebooks. Probably a lot of you have already run Jupyter Notebooks and you're thinking, why do I need to be taught about this? But most of the time when you run a notebook, they're not secure. It's HTTP. By default, Jupyter launches without security. There are some ways to make it more secure, and that's what we're trying to work on today. So there are vulnerabilities. In fact, the portal that Suba presented to you, the team spent the last year improving the security model. So we're working on that with our security expert, Scott Sakai, and some other people. So why is this a problem? The connection by default is not secure. You can connect over SSH tunneling. It's secure, and we have a little tutorial, and we have no problem with that, but it's inconvenient, and things happen like your connection may time out and you lose your notebook. So it's not the best way. So we've been trying to find something a little more optimal, and we came up with this idea of a reverse proxy service. So I'll show you how that works. And then Marty's been developing Galileo, which is a remote notebook launcher that would run off your laptop. Hopefully we can work on that and roll it out next year. So we allow Jupyter services, that's Jupyter Notebook and Jupyter Lab, to run on interactive nodes, on the compute nodes, on GPU nodes. So what's wrong with the default Jupyter Notebook? It helps to understand that you're on your laptop, you SSH over to the server, whichever, it could be the login node, which we don't want you to do, or even the remote node that you get with an interactive command. The Jupyter service launches, and it's a web server basically running for you on that node, but it's HTTP. So you have a secure SSH connection. Everything you type there is protected, but the connection between your web browser and Jupyter is insecure, which means it can be hacked. And so we're trying to overcome that by making this a little more secure. SSH tunneling works this way. What you do is you connect, you set up the tunneling by making a proxy connection between using the port. You set up a port on your laptop, a port on the Jupyter Notebook, and then an SSH connection between that port on your laptop and that port on the notebook, and everything communicated here, it's secure. But like I said, if you have some interruption, these things have a way of timing out, of getting disruptive. It's not very stable, but it works, and we're fine with you using that. So what's more secure is what we've architected in called the reverse proxy service. So you log in to Comet and you run a script, and the script will go and submit a request to the batch queue, grab an interactive node for you, launch your Jupyter service, either notebook or lab, and communicate with a reverse proxy service. And what you get back is an HTTP connection. So everything you do is encrypted. That's just basically, repeating what's in that diagram. The start Jupyter script is what you're going to run. You'll check it out and clone it from the repository. And you have arguments. You can tell it the partition you want, what directory you want it to start in, the project allocation. The batch script, do you want to use Notebook or a Jupyter Lab? Right now, you have to tell it a little more explicitly, but we're working on improving that part of the user interface, how long you want it to run, and you can get extra information about the job as we build the script and submit it. So to install it, I usually put it in a little working directory. You clone the repository and it gets installed, and then you come down into the directory and you'll see this script here. We've generalized the service so that it can work for systems that have Slurm or Torque, which means it works on Comet, Expanse, TSCC, Stratus, and we can just add, all we have to do is develop the right notebook configuration for the particular service. So you're just going to run this. All you have to do is run that script and the defaults will get picked up. Here's an example of starting it. You'll get some output. And one of the things that comes out is your notebook is here. So you want to copy that URL, paste it into a web browser, and you'll be given a monitoring window. And when it's finally launched, and that can take some time because the queuing system might be very busy, you'll get your notebook or your browser. And this is over here is just a little example of the script going the wrong way. And this is an example of using the Expanse portal to launch the notebook. So you log in and you pick a terminal window. And so what you get is a shell. And there's a link on this portal when you first log in. And you're in your shell. And what I did is I went into my reverse proxy and I typed start Jupyter. And by default, that's going to launch a notebook for me. And I got back a URL. I pasted it in and I monitored it. And then it ran. And so eventually, but it can take a while for it to run. So you can do it through the portal, or you can do this through the command line, whichever you want. And I think I'm in my time. Yeah, I think we still have time. All right, thank you. That's it. If you have any questions, if you have, this is a new product, a new application. So if you discover problems with it, please submit a ticket to Exceed Consult so we can make it work better. And that's it. Thank you.
Thanks, Mary. That was great. And last but not least, thanks everyone for hanging in there. Nicole Wolter will share some details on data transfer mechanisms. Nicole, are you muted?
I'm sorry, I just saw that. I apologize. So for this final thing, we'll talk about data storage and transferring. I'm going to do a quick overview of the storage we have available and the policies that are associated with it. I know that Mahi has discussed this previously, but it is a pretty big change. And so I think it's important that we drive it home to you that it's coming. And then I'll talk about some various options and tools that are going to help you manage how to manage the data you have. All right, so like on Comet, we have the home file system and then we have the parallel global file system. The home file system, similar to Comet, all users will get one. You will have 100 gigs of data there. I think both Marty and Mahi mentioned that this should only be used for scripts, maybe source trees, maybe binaries, static stuff that you want to keep forever. You should never run jobs from the home file system. One of it is that your performance isn't going to be that good. So instead, we recommend you use the parallel file systems. We have the Scratch and projects. As Scratch indicates, this is supposed to be temporary. On Comet, we recommended that it should be less than 3 months or less than 90 days. On Expanse, we're gonna help remind you that this is Scratch, and we're gonna automate that purge to help everyone. And it's gonna be 90 days from file creation. The other option we have, so again, any files that you have there that need to be in a little bit more permanent place should go into projects. Projects is actually allocated space, but all projects will by default get 500 gigs of memory. If you want any additional, or if you need additional space, as Mahi mentioned, you're going to need to justify it and either put it in your initial proposal or request a supplement. The other really, really important thing is that the Lustre file system does not have backups. So all the tools I'm going to talk about after this, please take advantage of them so that we never have a problem of that I've lost all my data. Since we know that we're not supposed to use login nodes, we shouldn't use login nodes for any compute or IO intensive. And the IO intensive is, of course, including moving large amounts of data. So we have 4 data mover nodes, and they're there specifically to help you guys transfer data back and forth. The data mover nodes can be used with all the tools that I'm going to discuss further. When you access, or you can access the data mover nodes with oasis-dm.sdsc.edu. I think that name might change, but at this time, when you go in there, it's load balanced so that it'll round robin to one of the 4 nodes. So there's, of the tools we have available, this kind of a list we have out there. When you're deciding on what tool to use, it's really going to depend on the amount of data that you have. So that includes both the size of the individual files and the number of files that you're moving. Other things that you kind of want to take into consideration is your workflow and if you need to be able to script any of these things. So if it's going to be scripted, you need a command line interface. So for smaller moves, you can use SCP or rsync or SFTP. For larger things, as Mahi mentioned, the Globus toolkit, we have a couple tools there and different places where you can use that from and how you can use it. In addition, we're kind of adding 2 new tools into our idea here because we're getting into the cloud a little bit more. You might be needing to move stuff off into archival storage. These tools are very robust and can help with other things. So we'll start with the small files. So for small files less than 2 gigabits, you can use SCP, SFTP, or rsync, but let's focus on the top 2 first. So SCP, is Secure Copy Protocol, is a utility for secure file transfer. SFTP, as Marty gave us a great example earlier, is Secure File Transfer Protocol. It has a utility with a bit more functionality. So not only can you transfer files, you can also access files and you can do some file management in there. With all these tools, there are lots of options of how you can use. I highly recommend, again, due to time, I'm cutting this very brief, but I recommend on the system, you do SCP help or command help, and it'll give you all the options that are available to you. Another thing to consider with these is that you can copy from a local site to a remote site, from a remote site back to your local site, or between 2 remote sites. Last tool I'm going to talk about kind of for these small is rsync. So rsync is going to be useful if you want to kind of maintain 2 equal copies on 2 different systems. The nice thing about rsync is it's not going to copy the entire file, it's just going to copy the changes that are happening, so it's a little less overhead for you. The next 3 tools I'm going to talk about rely on the Globus toolkit. The Globus toolkit is a collection of clients and middleware that is designed specifically for enabling technology for grid computing. So essentially allows secure communication between grid users that cross organizational boundaries. It's a command line tool that supports the standard SSH and grid. So you can use this in the single sign-on hub, but that's what it's using. It uses GSI SSH to interface with Globus. The transfer tools that are in there are GSI SCP and GSI FTP, and they're essentially the same as SCP and SFTP. The one thing with all the Globus tools is that you're going to need an active, that's important, exceed allocation. If you are a local user who only has a local allocation, feel free to contact us. In addition, if your account has expired, at this time, I believe if your allocation is over, exceed cuts you off. I believe they were talking about changing that, so there was a little bit of a leeway. But in case that's still the case, you should contact us either through the Exceed ticketing system or the SDSC local ticketing system. and will help facilitate it so that you can move your data as needed. If you're uncomfortable with the command line, you can use Globus via GUI. You'll log into www.globus.org. You're going to use your Exceed credentials to get in there. The endpoints are important, so you can see the collection is where you will select your endpoints. If you just start typing Exceed, it'll give you a full list of everything's in there, and you can pick and choose. Another thing to keep in mind is that the paths in Globus or on the data mover nodes are a little different than what is actually on the system itself. So check in the user guide to find how those paths, how they correlate between them. The next one I'm going to talk about is Globus URL copy. This can be done on the data mover nodes. It's a command line interface for high-speed data transfers. It also uses the grid FTP tool. So this is really recommended for large files and large number of files. So do a little segue here. Just because you can do something doesn't mean you should. If you have a large number of really small files, it is highly recommended that you tar them up and send them as one large file rather than lots of little files. So to use Globus URL copy, once you're on the data mover nodes, you need to load the Globus module. You need to check to make sure you have an active user proxy. The command is grid proxy info. It can tell you if it's available, how long it's available. By default, I think the certificates last for 12 hours. If you don't have one, you can use the command myproxy logon to create a new certificate for yourself. Again, the help --help will give you all the parameters to help you improve performance and to make this as efficient as possible. I should take a moment and note that the Globus toolkit can be up to 8 times faster than using SCP for large files and like the terabytes and stuff. However, it should also be noted that if you're doing really small files, it's actually better to use SCP because the grid tools will take longer because of the overhead associated with them. So now I'm going to talk about two tools that I am by no means fully versed in all their capabilities. These are 2 extremely robust tools that are way beyond just copying files. The first one is IBM Aspera. And the tool or the command that we use is ASCP. It uses a FASP technology to transfer and share files. It does a whole lot more. So it's for big data transport and syncing. You can send, you can share with this. It also helps with automation. And again, this can be used for the cloud stuff as well. I have a simple example here that's just kind of the high level, but again, lots more information, lots more functionality that's available with this tool, and you can find that at the link provided below. The IBM Aspera copy tool is currently available on the data mover nodes. So the AWS command line interface is not available yet. You would need to download it to use it. However, the instructions is super simple. So it comes down. It takes a little bit of time because it's a larger thing, but it's very simple. It's an open source tool to interact with the AWS services using commands in your command line shell. It'll use Linux. You can use it with Windows as well. It uses FTP or FTPS or SFTP to transfer stuff. Again, it's a very, very robust tool. There's a lot more options available out there, and you can find them by going on the web and checking it out. So we'll start with back up all your data. I remind you that we don't back up the Lustre file system. So it's really important that you take it upon yourselves to back up the data. And then kind of in review, there's lots of tools available on Expanse for data transfer. How you choose which tools to use is going to depend on the size of the files, the numbers of files, and what your workflow is. You should always avoid moving a lot of small files. There's an automated purge on the Lustre file system. So again, back up your data. And finally, we have mentioned that Comet's going to go away at the end of March, which means its file system will go away in mid-April. So we strongly encourage you, if you have a lot of data, to start thinking about where that data is going to go. Something else that I should mention that's a difference between Comet and all the resources before and Expanse is that Comet had the same home directory and actually loaded, I think, the file systems from previous. We aren't doing that with Expanse. So anything in your home directory, if you want it on Expanse, if it was on Comet, you're gonna need to copy it over. So, and I think that's all I have. Are there any questions, or I'll stop sharing and check the, lots. Yes.
Hey, everybody, I guess we're done and we're going to end on time, which is always good. Somebody asked about the presentations, so I'll post this again in the chat, but we'll have everything uploaded as PDFs in this directory. So thank you very much for attending. We really appreciate it and hope you found this helpful. We'll repeat it again in the spring before Comet shuts down. Send us questions, send questions to help@exceed.org if you have questions, consult or help@exceed.org if you have any other questions. Anybody have any comments or questions? Go ahead.
I just want to add that this being a 3-hour recording means it'll take a day or two at least to clean up the transcript and get it online. And we'll make the chat available and the slides as well. And there will also be a link. There's the link to the GitHub repository, and that'll be populated with additional resources as well. So thanks very much, everyone, for hanging in there. Thanks to the presenters. Thanks to the team for helping out on the chat too. Have a great day.
Yeah, have a great day, folks. Bye.
Thanks.